Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. Imagine yourself lying on a soft meadow on a clear night, far from any city lights. The air is cool against your skin, carrying the faint scent of grass. Above you, the sky is a black, velvet dome sprinkled with countless stars. The Milky Way arches overhead, a pale river of starlight. In this quiet moment, you feel deeply connected to the cosmos. The same space that stretches between those stars also surrounds you. A gentle breeze brushes your cheek. It moves through the night and through the space around you, here on Earth. As you gaze upward in comfortable silence, more and more pinpoints of light emerge, a glittering mosaic against eternity. You realize that when you look at these stars, you are literally looking back in time. Their light has traveled for hundreds or thousands of years to reach your eyes tonight. Some of those stars may have already lived out their lives and vanished, yet their glow still journeys onward through the dark to greet you here and now. You feel the solid earth beneath you and know that it too is suspended in that great darkness, a small, warm world afloat in an ocean of space. Yet you are not afraid. The darkness above feels inviting, almost comforting, like a vast shelter. The endless sky, rather than making you feel insignificant, fills you with peace and wonder. In the silence, you sense with gentle certainty that you are a part of this grand universe. The starlight that falls on your skin, the space that cradles your body, the photons entering your eyes, all of it binds you to the cosmos. You close your eyes for a moment. Behind your eyelids, the after-image of the stars dances in little sparkles. You take a slow breath in, and as you exhale, you let any tension flow out of you and into the vastness around. There is room for all of it to dissolve. There is room for everything in space. The universe is so wide and forgiving that your own cares begin to feel lighter, quieter, soothed by the infinite calm. Now, in that spirit of tranquility, let us embark on a journey into space itself. The space around us, the space within us, the space that is the foundation of all things. We begin where we are, in stillness, in the darkness, in the quiet. The night is profound and motionless. Above, the stars shine as tiny islands of light in a vast sea of black. Space stretches endlessly between and beyond them. This scene feels serene and timeless. Nothing stirs. No breeze now, no sound at all, only a gentle hush, the natural silence of a cosmos at rest. It is as though time itself has paused. You can almost feel the depth of this silence, a soft, velvety silence that blankets everything. The emptiness around you seems to embrace you with a subtle, invisible presence. For ages, we humans looked at the night sky and found it peaceful, but also mysterious. What is this blackness between the stars? We used to think it was nothing, an empty void, an infinite vacancy. People spoke of the void and the vacuum as if it were a true nothingness. We even doubted whether a true vacuum could exist at all. Ancient philosophers imagined that space must be filled with something. Aristotle believed nature abhorred a vacuum. Later, scientists in the 19th century hypothesized an invisible ether filling space to carry light across the emptiness. But experiments showed no such ether was needed. Light moves through empty space itself. This was a remarkable discovery. The void can carry light, as if emptiness has its own solidity. It hinted even then that space is not simply an inert backdrop. For a long time, though, the common view of space remained that it was a passive emptiness, a gargantuan container in which the objects of the universe, planets, stars, galaxies, are scattered. We pictured space as a stage and the stars as actors upon it, with no real influence from the stage itself. If you removed all the actors, the stage would just sit there, blank and silent. We imagined that if you took all matter away, you'd be left with pure nothing, an absolute void, infinite and eternal. Over time, however, our understanding evolved dramatically. We learned that space is far from nothing. That black backdrop, that stillness and silence, is deceptive. Space has properties, a structure, a dynamic of its own. In the past century, every new discovery has reinforced this truth. Space can bend. Space can carry light and soundless vibrations. Space can stretch. It can even boil at the tiniest scales, flickering with unseen energy. What we once thought of as an empty stage is more like a participant in the cosmic play. Tonight, as you float in this quiet moment, the darkness around you is not dead or inert. It is the very fabric that connects and supports all things. Let's explore this step by step, gently and thoroughly, starting with one of the most profound revelations, that space and gravity are intimately linked. Beneath you, the Earth's mass is pulling you down, or rather, it's warping the space under your body so that down is the direction you naturally fall. Above you, the Moon is held in its orbit by the shape of space around Earth. This understanding comes from Einstein's great insight in the early 20th century. Gravity is not a mysterious force acting across empty distance, but a feature of space and time itself. Mass and energy tell space how to curve, and the curvature of space tells objects how to move. In essence, matter sculpts space, creating valleys and hills in the fabric of space-time, and objects simply roll along those curves. What you feel as gravity, the weight on your back as you lie in the grass, or the pressure of your body against your bed, is actually space itself pushing you downward, guiding you along the curved lines it has formed around the Earth. To visualize this, imagine space as a vast elastic sheet spread out under the stars. If you place a heavy object on that sheet, say a bowling ball to represent a star or planet, the sheet will dimple, sagging inward around the weight. Now, if you roll a marble nearby, representing a smaller object like a planet, the marble will no longer travel in a straight line. It will spiral around the bowling ball, caught in the curve. In reality, Earth orbits the Sun because the Sun's mass curves the space around it, creating a sort of well that Earth is rolling around. Earth thinks it's moving in a straight line, and indeed it is, locally, but space itself is curved, so straight for Earth is actually a loop around the Sun. There is no gravitational force pulling Earth in a literal sense. Earth is simply following the path allowed by the curved space, like a ball rolling around a curved bowl. All planets, all moons, all orbiting bodies are doing the same. They are not tethered by invisible strings. They are skating along the contoured roads of space. Right now, as you lie still, you are held to the ground by this phenomenon. The mass of the Earth has curved space under you such that down points toward Earth's center. Your body presses into the ground because space is telling you to move that way. The ground pushes back and holds you up. Space does this quietly and continuously. You feel the effect as weight, but really, it is space-time gently urging you along a curved path that the solid Earth prevents you from taking. If Earth were not here, that curvature would extend unopposed. You would fall freely along a path through space toward where Earth's center was. All of this happens with no sound and no drama. Space does its work quietly. In essence, what we experience as gravity is the shape of space around us. Matter, like the Earth beneath you, tells space-time how to curve, and that curved space-time tells matter how to move. Gravity is not something that reaches out through space. Gravity is space. The stillness around you, in fact, is full of these invisible curves and subtle depressions wherever there is mass nearby. If you could see the geometry of space, You'd see gentle indentations around every tree, for even small objects curve space a tiny bit. Deeper wells around the mountains, and a huge well under your body, reaching to Earth's core. But space does its job so smoothly that you don't notice anything odd. You just stay attached to Earth as naturally as a leaf rests on the ground. This idea also means that when a massive object moves, it can create ripples in the fabric of space. Much like a stone dropped in a pond sends out waves on the water. Imagine two massive stars circling each other rapidly, or better yet, two black holes, extremely dense objects, spiraling together. They disturb the space-time around them so much that waves of curvature spread outwards. These are called gravitational waves, literal ripples of space traveling at the speed of light, washing through the cosmos. For a long time, we weren't sure these ripples really existed, but in recent years, scientists built instruments so sensitive that they could feel space-time tremble. When two distant black holes collided and merged in a galaxy billions of light years away, our detectors on Earth quivered ever so slightly. Space itself stretched and squashed by a tiny amount, far smaller than an atom, as the gravitational wave passed through. We heard the universe whisper through space-time. It was as if the stillness briefly sang a faint melody. Think about that. We built a device that can sense the movement of space from events that happened billions of years ago in far-off corners of the universe. When we detected those waves, it confirmed that space-time is not just an abstract idea. It's a real, physical fabric that can carry vibrations. Space can ring like a cosmic bell, even though we cannot hear it with our ears. In September 2015, when those two black holes merged, the fabric of space around Earth oscillated subtly, and our instruments recorded the telltale chirp. It was a triumph of human curiosity and a profound validation of the idea that emptiness has structure. The silence of space isn't absolute. If you have the right ears, space can indeed be heard. What an elegant picture, space as an ever-present elastic medium, carrying both the weight of stars and the whispers of their collisions. In summary, matter tells space-time how to curve, and space-time tells matter how to move. Gravity is not a pull through some void. It is the gentle guidance of objects along the contours of space-time. All of this, the Earth holding you, the Moon orbiting Earth, Earth orbiting the Sun orbiting our galaxy's center, is happening because space itself is shaped by mass and energy. Our everyday experience of weight is actually our intimate connection to the shape of space. So, from the stillness of space arises what seems to be a force, but space has more surprises. We've talked about space's shape. Let's now consider its unity with time. When Einstein described gravity as the curvature of space-time, he was saying something equally profound about time. That time is woven into the very fabric of space. Out in this quiet night, space and time seem separate. You can point in directions, you feel time passing. But experiments and theories show that they are inextricably linked. If you move fast or sit in a strong gravitational field, your experience of time changes relative to someone elsewhere. Space and time together form a four-dimensional weave, and gravity is the bending of that weave. Consider that the passage of time on the surface of Earth is slightly slower than time far out in space, because Earth's mass not only curves space, but also warps time. A clock on a mountain, where gravity is a tad weaker, ticks a little faster than a clock at sea level. Likewise, a clock on a fast-moving spaceship will tick slower than one on Earth. This isn't science fiction. We've measured it with precise atomic clocks. Even the GPS satellites in orbit must correct for time running faster up there. Weaker gravity, so faster time, compared to ground. Otherwise, their positioning would drift. What we find is that space and time adjust together. If space is squeezed or stretched, time is also altered. They are two aspects of a single entity, space-time. Think of space-time as a fabric with both spatial threads and temporal threads interwoven. You cannot disturb one without disturbing the other. When the sun's mass curves space-time, not only does space get warped, but time runs a bit slower near the sun compared to far away. An astronaut near a massive object ages a bit less quickly than one floating in weaker gravity. This is called gravitational time dilation. Similarly, if you travel at a speed close to light, time for you will slow relative to those you left behind. There is a famous thought experiment. Imagine twins, and one goes on a near light-speed journey to a distant star while the other stays on Earth. If the traveling twin returns after what she feels was perhaps a few years, she might find decades or more have passed on Earth. Her clock and body experience time more slowly due to her rapid motion through space-time. This isn't just a story, it's a real effect, verified by many experiments with particles and precise clocks. All of this tells us that space and time are not the separate, absolute backgrounds we once assumed. There is no universal time ticking the same for everyone, regardless of their state of motion or gravity. Instead, every observer has their own passage of time, depending on how they move through space and how space is curved where they are. Two people reunited after following different paths through space-time will have experienced different durations. What an astonishing reality. Time itself is elastic, flexible, personal. So here, under the stars, when you consider a moment of time and a stretch of space, realize they are part of one four-dimensional continuum. Here and now are bound together. You cannot point to a location in space without also specifying the moment in time. Everything that happens in space-time. The unity of space and time frames all experience. Right now, your heartbeat and the position of the moon both have coordinates in space-time, and gravity is the geometry of that space-time linking the two. Space and time are fused like two threads of a single fabric. Move fast through space, and you skew your passage through time. Stand in strong gravity, and time for you will run a bit slower than for someone far away. This interplay might sound complex, but think of it this way. Space alone isn't the full stage, and time alone isn't either. Rather, events unfold in space-time. If you try to separate them, you lose part of the picture. Even this peaceful moment has a space-time coordinate. You, here and now, under the night sky. As you lie there, time flows a tad differently than it would if you were orbiting the Earth or sitting on the moon, because the gravity and motion differ. The differences are small but real. Space-time enfolds you, ensuring that your now and here are connected into the grand tapestry of cause and effect that makes up reality. The important takeaway is, space and time are one fabric, and gravity is the bending of that fabric. The stillness you feel includes both space and time quietly doing their work. There is a timeless quality to this night because space and time together create that sensation. In this eternal present, you are embraced by space-time, which gently carries you along the stream of time while holding you in the structure of space. We have journeyed outward to see that what we thought was emptiness actually shapes the cosmos, and journeyed inward to see time intertwined with space. But the rabbit hole goes deeper. We must now explore the nature of space at the smallest scales, far smaller than a grain of sand, smaller than an atom, where an entirely new picture emerges. One might expect that if you zoom into space closely enough, you would eventually find absolute stillness and uniformity, perhaps even true nothingness. But our current understanding, through the lens of quantum physics, says otherwise. On extremely tiny scales, space is anything but smooth and still. It is frothing and fluctuating, buzzing with ephemeral activity. Physicist John Wheeler poetically called this the quantum foam. To grasp this, imagine shrinking yourself down beyond the microscopic, beyond the level of atoms, to a realm billions of times smaller. If you could stand there, if the word stand even makes sense at that scale, the the tranquil emptiness you perceive at our scale would vanish. Instead, you'd witness space seething with spontaneous eruptions of energy. Particles would blink in and out of existence like fleeting sparks. Distances and directions would blur as uncertainty reigns. In quantum physics, even what we call a perfect vacuum, completely devoid of matter and cooled down to remove all heat, is not truly empty. There is a fundamental jitter that cannot be removed. This is because the laws of quantum mechanics tell us that certain pairs of physical properties, like energy and time, or position and momentum, cannot both be known with infinite precision. There is a built-in uncertainty, and because of it, a vacuum cannot have exactly zero energy for all time. If it did, we'd know both its energy, zero, and that it stays that way, no fluctuation, forbidden by quantum rules. Instead, the vacuum seethes with what we call zero-point energy, a baseline, irreducible energy. What does this mean in practice? It means that empty space is constantly witnessing tiny particles flickering into being from nothing, then vanishing almost immediately. These are often called virtual particles. For example, a particle of light, a photon, might momentarily pop into existence, along with a counterpart, perhaps an electron-positron pair, borrowing energy from the vacuum for a brief instant. They appear, exist ever so briefly, and then annihilate each other, paying back the energy. All of this happens on timescales and distances so small we normally have no way to detect it directly. But it's happening everywhere, all the time. The space around you, between you and the next breath of air, between the electrons and nuclei in your body, between the Earth and Moon, is awash in these quantum fluctuations. On the scale of the unimaginably small, much smaller than an atom's nucleus, space-time would not look like a smooth sheet. It would look like a turbulent ocean surface in a storm, full of random waves, bubbles, and wrinkles, hence quantum foam. One moment, a bit of space might have slightly higher energy, sprouting a virtual particle-antiparticle pair. An instant later they collide and disappear, leaving a slight vibration of energy that then might spawn another pair elsewhere. Space at that level is a riot of spontaneous activity, an invisible, high-speed flickering that averages out to a seemingly smooth, stable whole at larger scales. We've even observed tangible effects of this quantum vacuum. If you place two metal plates extremely close together in a vacuum, just a few nanometers apart, they will experience a tiny force pushing them toward each other. This is the Casimir effect, and it happens because the quantum foam between the plates is slightly different from the foam outside. Certain virtual particle wavelengths can't exist in the narrow gap, so there is a tiny imbalance, fewer electromagnetic modes between the plates than outside. The result is a subtle pressure that nudges the plates together. In essence, the empty space between the plates has less quantum activity than the space outside, causing them to be pushed inward by the more energetic fluctuations outside. It's a small force. You'd need sensitive instruments to measure it, but it's real and has been observed. It's as if the vacuum between the plates is not nothing. It exerts a gentle push. This is a direct demonstration that empty space is never truly empty. The vacuum is alive with energy and possibility. In particle physics experiments, we also see clues of the quantum vacuum. For instance, empty space can briefly lend energy for the creation of particle pairs that affect processes like nuclear decay. The very fact that protons and neutrons inside atomic nuclei can change forms via quantum fluctuations involving ghostly particles is tied to vacuum activity. Even the stability of atoms and the patterns of atomic spectra bear the imprint of zero-point energy. So, as incredible as it sounds, the takeaway is that emptiness is not truly empty. It's an active medium. The stillness we perceive is actually a frenetic dance at microscopic scales. The vacuum is constantly borrowing energy here, giving it back there, in accordance with quantum uncertainty. Put poetically, Even when nature whispers hush, there remains an undercurrent of subtle noise, a quiet fizz of existence and annihilation on the tiniest scales. The concept of nothingness has been forever changed by this discovery. Empty space is a cauldron of potential, a field of fields, a stage for ceaseless miniature drama. If you were to shrink down into that realm, as a moment's imagination, since physically we cannot, you might see space flicker with tiny flashes, the foam that Wheeler described. It wouldn't be placid or uniform, it would be dynamic and random. The notion of a sharply defined point in space might lose meaning, blurred by these fluctuations. We sometimes say space-time becomes quantum foam at the Planck length, about 1035 meters, far smaller than any particle. At that scale, the smooth geometry of space-time breaks down into something probabilistic and fluctuating. Let's take a different kind of imaginative journey to appreciate this. Inward, into the fabric of matter and space inside you. Envision shrinking yourself, as we did under the stars, but now not in distance outwards, rather in size. You diminish down past the scale of dust mites, past cells and their nuclei, past even viruses and DNA molecules. Now you are smaller than an atom. Ahead of you floats a single atom of carbon from your body. It appears enormous from your current perspective. You approach it like a tiny spaceship nearing a planet. The atom consists of a blurry sphere, that is the cloud of electrons orbiting the nucleus. As you draw closer, this cloud is mostly transparent. You realize the electrons are tiny points moving so fast, they form a diffuse shell. You dive through this wispy shell of electron probability and find yourself in the interior of the atom. Suddenly, you are in what seems like a vast cavern. It feels eerily similar to drifting in space between stars. It is dark and almost empty. You might even see a faint glow of energy fluctuations around. The quantum foam flickers here too. For a moment, it's as if you're floating in a miniature version of outer space, a huge volume with almost nothing in it. Ahead, after some distance, you see a tiny but brilliant object, the atomic nucleus. You move toward it. What before was the immense atom is now mostly behind you. All that's left ahead is that nucleus, a cluster of protons and neutrons tightly clumped. It's small, incredibly small. If the whole atom were a cathedral, the nucleus would be like a single grain of sand at its center, and yet, that grain of sand holds almost all the mass. You come right up to the nucleus. It's made of particles bound together, busy with internal motions, but you cannot linger. At this scale, forces are intense. You decide to zoom back out. When you return to human scale, you carry with you a profound appreciation. Inside every atom in your body, between the electrons and the nucleus, there are enormous stretches of empty space. In fact, nearly all of the volume of each atom is empty. The solidity of your body, of the ground, of this meadow, it's an illusion created by the electromagnetic forces of electrons repelling each other at those tiny distances. No two atoms ever truly touch in a physical sense. Their electron clouds push against each other first. Matter is a scaffold built on emptiness. It is astonishing. All the solid things we see around us are about 99% empty space. If one could magically remove all the empty space within the atoms of your body, compressing the electrons into the nuclei, you would shrink to a microscopic speck, smaller than a pinhead, yet you'd weigh the same as you do now. By some estimates, if we removed all the empty space from all the atoms of all humans on Earth, the entire human race could fit into a volume the size of a sugar cube. It sounds impossible, but it's because atoms are so vast compared to their tiny nuclei. Nature itself offers a demonstration. In neutron stars, the remnants of large stars, gravity crushes atoms so hard that electrons and protons merge, eliminating that atomic emptiness. A single teaspoon of neutron star material can weigh billions of tons. That's how much stuff was hiding in the empty space of atoms. When that space is removed, matter's true density shows. Fortunately, here on Earth, our matter stays spacious, our atoms intact with their generous voids inside. Take a moment to let that sink in. Solidity is an illusion. When we say an object, a rock, a chair, your own body, is solid, we're talking about the collective sense of touch that arises from trillions of atoms whose electrons resist being pushed into the empty space of one another. It is like a lattice of charged particles, and their mutual repulsion gives structure and firmness. But the structure is mostly empty space. We and the world we live in are made of a whole lot of nothing. It's a humbling realization. You are a being composed almost entirely of voids, shaped by forces and energy into the form you call you. In a very literal way, you are a small universe of particles orbiting each other in vast fields of emptiness. Now we have explored the microscopic character of space, the quantum foam and the atomic void. We've seen that even when matter is present, it's built on a framework of emptiness, and even when nothing is present, space is still far from idle or empty. The calm void of night harbors deep activity at tiny scales and comprises the majority of the volume of any solid thing. Space pervades every corner of existence. It is above us in the cosmos and within us in each atom. Let's step back out to the cosmic scale again. We've marveled at gravity and quantum foam and the space within atoms. But what about the shape of the universe as a whole? Does this infinite darkness go on forever? Does it curve back on itself like the surface of a planet? These questions have intrigued humanity for as long as we've looked up and wondered. Is space infinite, or is there some kind of boundary or loop? With modern science, we have attempted to measure the geometry of the universe. The answer isn't fully in, but so far it appears that on the larger scales we can observe, space is extremely flat and likely unbounded. By flat, we mean it follows the rules of Euclidean geometry, the sums of angles in triangles, etc., as far as we can see. If space had a noticeable curvature, we would detect distortions in the patterns of galaxies or the light from the early universe. The results? All measurements indicate that space is extraordinarily flat on the biggest scales. If there is curvature, it is so gentle that our observable universe, a sphere of about 93 billion light-years in diameter, doesn't reveal it. To use an analogy, Earth appears flat to someone walking a few miles because it's so large that the curvature isn't obvious at that scale. Similarly, the universe might be curved in some way, but on the scale we can survey, it looks effectively flat. What does flatness imply for the extent of space? It suggests that space could be infinite, extending forever in all directions, or it could be finite, but without boundary, like how the 2D surface of a sphere is finite area, yet has no edge, except extended to three-dimensional space. If space has positive curvature, like a 3D sphere, it would be finite in volume, and if you traveled far enough in one direction, you might eventually end up where you started, just as an ant crawling on a basketball eventually loops around. If space has negative curvature, like a saddle shape, it would be infinite and spread out with a different geometry. A flat universe, the simplest case, can be infinite and just go on and on. Current data lean toward flatness and therefore possibly infinitude, or a curvature radius so immense that for all intents and purposes it is infinite to us. From what we can tell, there is no edge to space, no wall where space ends. If it is finite and curved back on itself, going in a straight line could, in theory, bring you back to your starting point after an almost inconceivably long journey. We have looked for evidence of light wrapping around the universe, like seeing the same galaxies repeated from opposite directions, which could happen if space were closed and not too large. But we haven't found any such patterns. If the universe is finite and closed, it's far larger than the volume we can see. If it's infinite and open, it just has no end. In either case, there's no boundary that says, beyond here, there is nothing. Space, as far as we know, either goes on forever or loops back on itself. The observable part, what we can see, is certainly finite, but that's only due to the limited age of the universe and the finite speed of light. Beyond that observable horizon, we expect there is more universe, probably much more. We can summarize our findings here. The large-scale universe appears flat and unbounded. Precision measurements of the cosmic microwave background, the afterglow of the Big Bang, by satellites and telescopes have narrowed any possible curvature to be extremely slight. So, space is remarkably flat as best we can tell. It might truly be infinite. It might wrap around on a scale so huge we haven't detected it. Either way, for our observable domain, Euclid's geometry holds to a high degree. Parallel light beams do not meet, and the angles of a huge triangle drawn by, say, beams of light spanning billions of light years seem to add up to 180 degrees. This is a clue that the cosmos, on the whole, is not shaped like a sharp sphere or saddle within our view. If it is spherical, the sphere is enormous beyond imagination. If it is saddle-like, the curvature is so subtle that we haven't discerned it yet. In our contemplative journey, lying here under the night sky, it's awe-inspiring to realize we've been able to figure this out at all. By observing distant galaxies and the patterns in the microwave background, humanity has effectively used the universe itself as a giant ruler and protractor. We map the distribution of galaxies and notice that on large scales, they form a sort of cosmic web, filaments of clusters and superclusters surrounding huge, nearly empty voids. Those voids, expanses tens of millions of light years across with hardly any galaxies, highlight again how dominant space is over matter. Matter forms a delicate lace, and space is the vast expanse between its threads. The cosmic web shows that even on the grandest scale of clusters of galaxies, emptiness stretches out between them, making up the bulk of existence. Indeed, when astronomers survey the cosmos, they see that galaxies are not evenly spread. They line up in filaments and walls, with enormous voids between. Those voids are truly empty regions, aside from perhaps the stray hydrogen atom here or there. Some voids span hundreds of millions of light years with essentially no galaxies inside. Think about that. Such a volume is mind-bogglingly large, and yet nearly completely devoid of stars, planets, or light. Just tenuous gas and darkness. Those cosmic voids are, in a sense, pure space on the largest scale, a testament to how predominant emptiness is. The luminous matter, galaxies, clusters, outlines like scaffolding on the tapestry of space, but the vast gulfs between that scaffolding are space itself, pristine and quiet. Now, our understanding of space wouldn't be complete without touching on one of the greatest mysteries of the cosmos today, the fact that the universe's expansion is speeding up. We mentioned earlier that the universe is expanding like a rising loaf of bread, carrying raisins, galaxies, apart. You might expect, intuitively, that this expansion would slow down over time. After all, gravity is pulling galaxies toward each other. Indeed, for a long while after the Big Bang, the expansion did slow as gravity reined it in. But to astronomers' astonishment, in the last few billion years, the expansion has begun to accelerate. Galaxies are flying apart faster and faster. There is something in space, some form of energy tied to the vacuum itself, that is pushing the universe outward. We call this strange phenomenon dark energy. The name is just a placeholder, really, a label for our ignorance. It was discovered in the late 1990s when two independent teams observed distant exploding stars, supernovae, and found them dimmer, and thus farther, than expected. It was as if, over the billions of years their light traveled, the space between us and those supernovae had stretched more than it would have in a decelerating universe. At first, this result was met with surprise and a bit of skepticism. Could the expansion be accelerating? That was contrary to everything we thought. Even Einstein, long before, had considered a static, or at most slowing universe. But one by one, other evidence accumulated. Detailed maps of the cosmic microwave background and surveys of galaxy clustering both pointed to the same conclusion. Some kind of repulsive effect is at work on cosmic scales. By the early 2000s, the verdict was clear. The expansion of the universe is speeding up. So what is dark energy? In short, we don't know. It appears to behave like an intrinsic property of space. Like each cubic meter of vacuum has a certain tiny amount of energy that doesn't dilute even as the universe expands. If that's true, then as space expands, you get more vacuum, and thus more of this energy, causing expansion to push even harder, a runaway effect, though fortunately a very gradual runaway. Roughly 2/3 of the universe's total energy content today seems to be this dark energy. Only about 1/3 is in matter, mostly dark matter, plus a few percent normal matter like atoms. That means most of what's out there is this mysterious energy of empty space. It's dark because we can't see it or touch it. It doesn't emit light. And it's energy in the sense that it does work on the universe. It's causing space to swell. We sometimes describe dark energy as a negative pressure or an anti-gravity effect of the vacuum. It's as if emptiness itself has a springiness, a tendency to expand. Every bit of empty space gently pushes outward on itself. The effect is extremely weak on small scales. It's completely overwhelmed by local gravity or even the forces binding galaxies. But on the vast scale where gravity's pull has been growing weaker as galaxies get farther apart, eventually this subtle pressure took over and started accelerating the expansion again. The concept of dark energy reminds us how much we still don't know. It humbles us. We see its effects, yet the cause remains elusive. It could be something fundamental about space that we have yet to understand, perhaps related to that quantum foam energy we talked about. Those straightforward calculations of vacuum energy don't match the observed dark energy. That's a huge puzzle in physics. It could be a new field or fluid pervading the cosmos, or an adjustment needed in our theory of gravity at large scales. We gave it a name, but naming is not understanding. Dark energy is truly a question mark at the heart of cosmology. In essence, what we know is this: empty space isn't just inert nothing. It has this property that is making the universe fly apart faster and faster. The same emptiness between galaxies carries an unknown energy that currently drives the fate of the entire universe. Far from being an irrelevant void, space, through dark energy, will determine how the cosmos evolves trillions of years into the future. To put it succinctly, something latent in empty space, call it dark energy, is accelerating the expansion. The void has a sort of built-in push. This discovery is as dramatic as when we first learned space can bend. It tells us that space has a mind of its own, so to speak, a propensity not only to warp when mass is present, but to grow even where mass is absent. It's as though emptiness has a gentle heartbeat, steadily pumping the universe larger. So now we have seen space from two extreme perspectives: the microscopic, roiling with quantum fluctuations, and the cosmic, swelling with dark energy. We've also seen space permeating matter in atoms. It is clear that space is not a passive backdrop. It's dynamic and rich. Let's recap our journey so far in simpler terms. Gravity taught us that space is flexible. It can bend, fold, and ripple. Relativity taught us that space and time are united. Quantum physics taught us that space is restless at small scales. It's never truly empty. Modern cosmology taught us that space can expand and carries a mysterious energy in its very form. And everyday life and atomic physics taught us that even seemingly solid matter is mostly space inside. Now, with these insights, consider what space really is. It's not empty. It's the very medium of existence. Space is the canvas on which the masterpiece of the night sky is painted, and also the paint and pigments in that masterpiece. It is the medium through which light travels, and also an actor that shapes the story, by bending light, for example, as in gravitational lensing, where space curves around a massive galaxy cluster and bends the light of more distant galaxies into arcs. Space is the connector between distant objects, the silence that allows a conversation via light or gravity to happen across cosmic distances. Space is the stage on which all cosmic drama unfolds, and yet it is also an actor, shaping the plot with its curves and expansions. It is the ocean on which galaxies sail and the gentle tide that carries them apart. Space is a teacher of humility. It shows us that even what seems empty can hold unimaginable power and significance. It reminds us that absence can be potent, that silence can speak volumes. The stillness of space, which once seemed like nothingness, in fact contains the code that dictates the evolution of the entire universe. When we consider the scale of space and how much of everything is made of it, we might feel small, but there is comfort in it too. Space is a comfort in its constancy. It's been here since the beginning and will be here long after the end of all things. When we feel overwhelmed by our day, we can look up and remember how vast and enduring the universe is. Our worries shrink in the face of that perspective, not to trivialize them, but to soothe us with the knowledge that we're part of something much larger and older, where many troubles have come and gone under the eternal sky. Even our ignorance, like the mystery of dark energy, is a kind of tribute to how subtle and profound space is. It's astonishing to realize that only a century ago, we didn't know any of this. We thought the Milky Way was the entire universe, and we believed space was just an empty void that played little role. Now we've learned so much, that the universe is expanding, that space and time bend, that there are countless other galaxies, that space can erupt with virtual particles and drive cosmic acceleration. Each discovery has only deepened the wonder. Knowing that space can ripple and boil and propel galaxies doesn't take away the magic of the night sky. It adds layers of awe to it. The more we comprehend, the more we appreciate how extraordinary it all is. Finally, let's ponder one more speculation that stretches our imagination to the limit. The possibility that our universe's space is not the only space. Could it be that beyond the observable universe, or in dimensions or contexts we cannot see, there are other universes, other expanses of space-time, disconnected from ours? In other words, a multiverse. This idea is highly speculative, yet many scientists consider it plausible given certain interpretations of cosmology and quantum theory. One scenario arises from cosmic inflation, the extremely rapid expansion that likely occurred fractions of a second after the Big Bang. Inflation might not have ended everywhere at once. It could be bubbling continuously, even today, in distant realms beyond our horizon. Each bubble that inflation drops out would become its own universe with possibly different properties. Our universe would be one bubble among potentially countless others in a frothing metacosmos. To visualize this, imagine stepping outside our universe, a mind-bending thought, and looking at a larger sphere of reality. You might see an eternally expanding space like boiling water, with bubbles forming here and there. Each bubble is a universe, perhaps with its own galaxies and laws of physics. Ours is just one bubble that happened to inflate and then slow down, allowing stars and galaxies to form. Some bubbles might remain forever separate, carried away by relentless inflation in between. Others might occasionally collide, potentially leaving subtle imprints. People have even searched our sky for patterns that could be from a collision with another universe bubble, though none has been confirmed. In this view, reality is far grander than what we can see, a multiverse of universes. Another multiverse concept comes from quantum mechanics, the many worlds idea, where every quantum event splits reality into multiple branches. In that interpretation, there is a vast ensemble of parallel outcomes, parallel universes coexisting in a larger quantum reality. If true, there might be another version of you in a parallel world, where some decision or event went differently. This is a different flavor of multiverse, more about layers of reality stacking on the same space rather than separate bubbles of space. But it underscores how space might be part of a much larger tapestry. Whether through cosmic inflation or quantum many worlds, or other ideas, like perhaps a cyclic universe that periodically resets, the multiverse remains a hypothesis. We have no direct evidence of other universes. We may never have. It is a mind-expanding possibility, essentially suggesting that what we used to call the universe, meaning everything, might be just a tiny piece of an even vaster existence. If it's true, it's the ultimate Copernican revolution. Not only are we not the center of the universe, but our universe might not be the only one of its kind. Just one bubble in an endless foam. Such a concept can be daunting, but it can also be oddly comforting. It would mean creation is endlessly fertile. That reality tries every possibility, that somewhere, everything that can happen does happen. It also could provide an answer to that question of why our universe has the conditions it does, why the constants of nature are fine-tuned for life. If there are countless universes with varying conditions, we naturally find ourselves in one of the rare universes that is compatible with observers like us. In a multiverse, our hospitable cosmos isn't a 1 in a billion fluke so much as an inevitability among infinite tries. We should stress that the multiverse is still speculative. It's an idea, albeit one that arises from serious physics theories, but we have yet to find a way to test or observe it. It remains a tantalizing possibility on the fringes of our understanding. Whether true or not, just contemplating it broadens our perspective even further. It tells us that space, that fundamental thing we've been exploring, might come in an endless variety of forms across different universes. Perhaps some universes have more dimensions of space, or different kinds of particles, or maybe no matter at all, just endless, empty space-time, expanding or contracting. The possibilities are endless. Even if the multiverse remains unproven, thinking about it does one certain good. It underscores just how precious our particular universe is. We have this vast cosmos to explore and understand, full of wonders like those we've discussed tonight. We might be essentially alone, with no other universes ever reachable, or we might be one among billions. Either way, our task and our joy is to know our universe as deeply as we can and find our meaning within it. Now, let us gently return to where we began, to the simple stillness of the night and the feeling of space around us. After journeying through curved space-time and quantum foam, across the cosmos and into the atom, we come back to ourselves, lying here under the sky, whether literally or in our mind's eye, quiet, at peace, and maybe a little wiser. The night is still as it was, but we are not the same. The darkness holds more meaning now. We can sense, behind the silence, the faint echoes of all those phenomena we've talked about. The whisper of space-time, the hum of the quantum vacuum, the faint pressure of dark energy, the quiet spaciousness within our very cells. The stillness around us resonates with the knowledge that it is not an empty stillness at all, but full of structure and story. Space is not empty. It's imbued with the fabric of existence. It connects everything to everything else. In this darkness, the light from distant stars travels. The space allows it to move at the fastest speed possible. The gravity of the Earth extends through space to tug on the moon. Fields, like the electromagnetic field, permeate space and allow radio waves, visible light, X-rays, all forms of light to propagate. Invisible geomagnetic fields from Earth reach out into space around you right now. Space truly is the medium in which all things exist, and through which all interactions occur. If it were somehow removed, all those interactions would vanish, and nothing could happen or even be. Consider some of the roles of space we've encountered. Space is the canvas on which galaxies paint their grand designs. and also the weaver that curves and folds itself to create gravity's effect. Space is the nurturer of structure. Its quantum fluctuations seeded galaxies, and its expanses gave them room to grow. Space is the arena of all history. Every event that has ever happened, from the birth of a star to the firing of a neuron in your brain, took place in space-time. Space is the ultimate connector. When you touch a loved one's hand, it's the space and electromagnetic force fields in that space, between the atoms of your hand and theirs, that communicates the pressure and warmth. Space is a teacher. It teaches us that what appears empty can be full, that absence can have presence. It is a guardian of the universe's secrets, hiding dark energy within itself, keeping the ultimate fate of the cosmos in its hands. And space will be the stage for the universe's far future. Looking trillions of years ahead, one can envision a time when space will be virtually all that remains. As the eons pass, galaxies outside our local group will drift farther and farther away, eventually vanishing beyond the horizon, their light stretched into oblivion by the expanding space. The night sky will grow emptier as distant stars disappear from view. Trillions of years from now, even the stars in our own galaxy will exhaust their fuel. One by one, they will wink out, leaving behind faint embers, white dwarfs, neutron stars, and black holes. These remnants will gradually cool and evaporate, in the case of black holes, via Hawking radiation, over an incomprehensible span of time. The universe will continue to expand and cool toward a state of almost complete darkness. In that far future, no new stars are born. No bright galaxies light up the sky. What remains is largely space itself. Vast, cold, nearly empty, studded only sparsely with subatomic particles and the fading whisper of photons from long ago starlight. And yet, through it all, space endures. The same fabric of space-time that was there at the fiery birth of the cosmos will still be there in that silent twilight eons hence. The stage persists even after the actors have left. Perhaps that will be the final chapter of our universe. An ever-expanding dark volume of nearly pure space, quietly extending into eternity. Perhaps, someday, quantum fluctuations within that nothingness might seed a new Big Bang, a new universe, a speculation in some cyclic cosmologies. But either way, the legacy of space is that it is the last cosmic witness. When all else has come and gone, space will still be here, silent and waiting, as it was in the beginning. Space is, in a sense, the alpha and omega of the universe, present at the start, shaping everything in between, and remaining at the end. Now, back to this moment. The night is deep and beautiful. The quiet around you, this gentle void, is the same entity we've been contemplating in all those extraordinary ways. Let that sink in. The empty air and space enfolding you right now carries the heritage of the entire cosmos. It carries the gravity that holds you to Earth. It carries the starlight that reaches your eyes. It carries the potential for future worlds and the echo of the very birth of the universe, a faint whisper of microwave background that bathes all of space, even now, at about 2.7 degrees above absolute zero, giving the night a slight warmth. This space around you is part of the same continuum that bends around a black hole and expands between galaxies and buzzes with vacuum energy. You are deeply connected to the universe through space. You always have been. It's impossible to be truly isolated because the fabric of space links you to the furthest galaxy and the smallest atom. When you look at the stars or simply breathe the night air, that connection only becomes more apparent. You are a child of space, born from stardust that coalesced in space, sustained every second by the oxygen and photons traveling through space. And ultimately, when you return to dust, your particles will drift in space again. Bask in that realization. You belong. You belong here in the universe, and it belongs in you. The boundary between you and out there is not a wall, but a porous membrane constantly exchanging matter and energy. You inhale the atmosphere, drawing in molecules that might once have been exhaled by ancient trees or dinosaurs, and ultimately originated in cosmic processes. You exhale, and your breath's atoms eventually mix into the sky and beyond. In a physical sense, you are never separate from the universe. You are always in communion with it. Take another slow, gentle breath. Feel the cool air fill your lungs, and know that even that simple act is an interaction with space. As the air spreads in your lungs, it's essentially molecules finding room in the internal space of your body, delivering oxygen to your cells across microscopic gaps. As you breathe out, you're releasing carbon dioxide that will travel through the atmosphere, maybe feed plants, maybe one day waft into the upper sky and beyond. Through you, the earth and space are linked. Now, you have permission to let go of all these thoughts if you wish. You don't need to actively think about curvature or quantum foam or dark energy anymore tonight. The knowledge is there, settled gently in the back of your mind, enriching the way you feel the night. You can simply relax in the feeling of it, the feeling of being part of this vast, ongoing cosmos. Above, the stars continue to shine, distant and silent. Around, the darkness remains calm and embracing. You might sense in your own body a mirror of the cosmos, the rise and fall of your chest like the expansion of space, the circulation of blood like galaxies drifting in their clusters, the neural flashes in your brain like tiny starbursts. In the stillness, you can almost feel the subtle humming connection between your life and the wider universe. You are safe, you are weightless and free. The quiet of space enfolds you like a warm blanket. Feel how the whole universe supports you in this moment, the ground beneath you, the air around you, the sky above. You belong here. You are part of all this. There is nothing you need to do right now except be. Just exist. Just rest. Inhale the stillness. Exhale any worry. Let yourself float on the calm of the cosmic ocean. You are safe. You are embraced by existence. You are at peace. No matter where you go, you carry this home of space with you. It was there at the first moment of your life. It sustains you each day, and it will remain long after we are gone. The stillness that surrounds you is the same stillness that cradled the young universe and that will hold the final stars as they wink out. You are truly home in this stillness. It is the cradle of everything. All the understanding we've gained about gravity, time, quantum foam, expansion, and so on, leads to a simple, profound truth. Space is not empty. It is everything. It is the foundation and framework of existence, and you are not separate from it. You are one with it. An expression of the universe, a part of space becomes self-aware. When you gaze at the night, the universe is gazing back at itself through your eyes. So rest now, gently, in the embrace of space. Feel the deep peace of knowing that you are held by the same darkness that carries the stars. The infinite extends around you, quiet and caring. Let go of any remaining tension. Let it fall into the vast well of calm that is space. Let your thoughts drift like gentle clouds across the sky of your mind. No need to chase them. They can float away into the darkness, leaving you calm and clear. You are safe. You are weightless. You are free. The endless silent universe enfolds you, and you belong to it. You are a part of it all, and it is a part of you. In this profound unity, you can release all fears and rest. The night is very quiet now. Around you, the earth sleeps, and the cosmos watches in patient silence. Feel your heartbeat slowing, peaceful. A tiny clock kept by space-time within you. Feel your breaths becoming soft and rhythmic, the same rhythm that pervades all of nature. There is no rush. Time flows at its own gentle pace. Space provides limitless room for your dreams to unfold. You are home in the universe. You are never alone. The space that fills your room, your lungs, and your heart connects you to the furthest galaxy and to the beginning of time. In this knowledge, you can truly rest. All is tranquil. All is as it should be. Stillness. The stars shine. The galaxy slowly turns. The universe breathes in and out on timescales far beyond comprehension. And here, in this quiet moment, you breathe softly, in unison with the cosmos. The stillness of space is within you and around you. Let it lull you into a deep and gentle sleep. Feel yourself drifting, weightless, on a calm, cosmic sea. There is nothing to fear in this dark. It is the same darkness that gave birth to the first dawn. There is everything to love in this silence. It carries the echoes of creation and the promise of eternity. You are safe, you are connected, you are at peace. Sink deeper now into the comforting dark. The universe holds you like a parent cradling a child. The ground beneath you, the sky above, all is one with you. Your mind is quiet, tracing the outlines of these truths with a final, drowsy sense of awe. What remains is not calculation or analysis, but a simple reverence for existence. In the grand sanctuary of space, you close your eyes, your breathing slow and steady. The boundary between yourself and the night dissolves. You are the universe, and the universe is you, a wave returning to the ocean of space. Rest now in that knowledge. Rest in the arms of the cosmos. Feel the profound stillness, the gentle, omnipresent support of space beneath you, holding you up as it has held up worlds and suns and galaxies. Let that stillness fill you. There is nothing more to do, no more striving needed. Just be. Just let yourself go, like a leaf floating on a vast dark pond, carried by the calm currents. Space will watch over you. It has always watched over everything. Your mind is calm. Your body is relaxed. The stars continue their silent vigil overhead, and you drift closer to sleep, carried by the same silence that spans the light years. The feeling of space, that stillness, that openness, that gentle cradle of all things is all around you, and it soaks into your very bones. In this moment, you are that stillness. There is no separation. Quietly, the universe whispers you a lullaby in the language of silence. It says, "You are home. You are home." Let yourself drift in this infinite peace, stillness, silence, space. The journey is complete. The knowledge is within you. The stillness is everything. You are a child of the cosmos, and the cosmos is kind. Feel its love in the quiet of the night. Space is not empty. Space is everything. And you, your atoms, your mind, your life, you are part of that everything. You always have been and always will be. In the great dark between the stars, there is comfort and belonging. In the stillness here, there is the embrace of the infinite. Be at peace, dear traveler of the universe. You are home in the stars and the night. The space around you is your space. The silence around you is your silence. Nothing separates you from the whole. You are safe. You are loved. You are one with the deep, eternal stillness of space. Rest now in that eternal stillness. Let the quiet carry you into restful sleep, as gently as a mother rocks a baby, as naturally as night becomes dawn. The universe holds you. Stillness, silence, sleep. Good night, child of space. The cosmos within and around you watches over you, now and always. Stillness. I invite you into the silence, a pregnant hush between moments, into the vast and boundless calm that lies behind all things. I am space, and I surround you completely. I am the darkness and depth between stars, sparkling like diamonds, the stillness between breaths, the expanse that holds every atom and every galaxy. In this moment of stillness, you ask, what am I? Long before you understood what I am, you looked up and filled me with stories. Often you gave me names and personalities: Nut, Uranus, Shu, the Heavens Father and Earth Mother, trying to understand my nature through myth and story. You sensed there was something powerful about the emptiness and silence above, something worthy of reverence. In ancient times, you imagined the sky as a dome overhead, painted with countless stars, a firmament just beyond reach. Earth, you thought, sat at the center of a small, orderly cosmos, and I was merely a backdrop, an upturned bowl decorated with lights. But over centuries, your perspective evolved. You discovered that the Earth is not the center, but a planet circling one star among billions. You learned that the stars are not holes in a dome, but distant suns scattered through a vast and boundless abyss. The more you learned, the more your conception of me transformed. From a finite vault above your head to an infinite expanse with depth and structure. What once was a comforting, closed sky became an endless ocean of space stretching in all directions without center or edge. Emptiness, it turned out, was not empty at all, but rich with secrets. I am not a simple void. I am more like a canvas, invisible yet ever present, holding the artwork of reality. Without me, there could be no separation between things, no here or there, no before or after. If I truly were nothingness, everything would collapse together with nowhere to be. It is I who give reality its form and scale. Some have called me a cosmic ocean, and indeed, I roll on endlessly. Galaxies can be thought of as boats, or even tiny leaves carried on my currents. Gravity is the tide that pulls and shapes, and light is the beacon that travels my waves. You, on your planet, are like a sailor on a small ship, just beginning to venture from the shore and grasp the true scale of this ocean. The ancients launched their imaginations into my depths with myths. You launch rockets and let telescopes sail my waters of space, discovering new horizons that only reveal greater and greater oceans beyond. Time itself started with my birth. Asking what came before is like asking what lies north of the North Pole. There was no before me, for without space and time, before and after do not exist. In the beginning, I was compact beyond imagining. In a flash of creation, I was born alongside time and energy. Back then, I was small, hot, and filled with potential. In fact, in my first split second, I likely underwent an extraordinary expansion, an inflation, swelling far faster than the speed of light, because no object moved through space. Space itself grew, and smoothing out the cosmos. What started as microscopic became cosmic almost instantaneously. After that initial surge, my expansion settled down to a more stately pace. As I expanded and cooled, the matter and energy within me began to coalesce. Tiny quantum tremors, random fluctuations in the fabric of reality, were stretched out with me. Those minuscule irregularities, mere whispers in the silence, would become the seeds of all structure. The galaxies and clusters and cosmic web of today trace their origins to those first faint ripples. For a long time, you humans saw me as static emptiness, but then you discovered my deeper nature. You learned that I can bend, curve, and ripple. Massive objects like stars and planets do not just reside in space, they deform it. Picture a heavy ball placed on a flexible sheet. The sheet stretches and curves around the ball. Similarly, when a star sits within me, I wrap around it, curving in response to its mass. This curvature is what you feel as gravity, though you once imagined gravity as an invisible force acting at a distance. It was a revolution in thought to realize this. No longer was gravity a mysterious pull through empty void. Instead, gravity became the shape of space itself. Mass and energy tell me how to curve. In turn, I tell objects how to move. A planet orbiting a star is like a marble rolling around the rim of a bowl, my bowl, gently curved by the star's presence. Planets circle not because of ropes or invisible strings, but because they are following the curves of space that mass creates. In this way, I cradle the sun and earth in an embrace of geometry, allowing worlds to orbit with no physical tether except the structure of space. Space and time are inseparable in this dance. I am space, but I am entwined with time, my eternal partner. Together, we form space-time, a unified fabric where every here is woven with a now. Under the weight of a star or planet, not only do I bend, but time itself slows down. When I curve strongly, time itself also slows and bends. We both warp together, threads of one cosmic cloth. Even on Earth, this effect is present. Time runs slightly faster high in the mountains than at sea level, where gravity is a bit stronger, and a clock on a fast-moving spacecraft ticks a bit slower than one on the ground. These differences are tiny in everyday life, but they become measurable with precise instruments, and they prove that time is not separate and absolute, but intertwined with space and motion. Picture a clock deep in a gravity well, near a massive planet. It ticks more slowly than a clock far above. If you lived your life on a mountaintop, you'd age a few microseconds more over a lifetime than your twin at sea level. If you flew in a fast rocket, your time would pass slightly differently than that of those you left behind. This isn't just fantasy. It's measured fact, evidence of how profoundly connected space and time are. Consider the extreme, a black hole. Here, space curves into a deep, steep well. If the mass of a star is crammed into a tiny volume, it bends space-time so intensely that not even light can escape the grip. A black hole is a place where space and time themselves break from ordinary rules. If you ventured towards such a black hole, you would hardly notice the exact moment you crossed its invisible boundary, the event horizon. But outside observers would see you slow and fade, never quite seeming to fall in. Space around you would funnel inward. Every path, every direction would lead down to the center. Escape becomes impossible because beyond that horizon, all routes point deeper in. At that center, the singularity, our known physics falters. It may be a point of infinite density, a place of zero volume where my curvature grows without bound. Or perhaps quantum effects soften the blow. We do not yet know. But certainly, whatever falls in does not return. In that hidden heart of a black hole, space itself flows inward like a rushing stream, carrying matter with it. These cosmic traps are like caves in my fabric, unseen directly, but sensed by their intense gravity. And when two black holes collide and merge, they send tremors through me, ringing the universe with their final merger. Yes, I can ripple like the surface of a pond. When massive objects move violently, stars exploding asymmetrically, or black holes orbiting each other, they create waves in space-time itself. These are gravitational waves, faint ripples that race across the universe at the speed of light. I carry these vibrations as a silent echo of distant cataclysms. For a long time, they were merely predicted, but not heard. Then, in recent years, you built instruments so sensitive that they could feel these tremors. In a quiet laboratory, lasers in long vacuum tunnels detected the subtle stretching and squeezing of space from two black holes colliding a billion light-years away. It was a whisper, a tiny chirp in the data, yet it spoke volumes, confirming that when the universe moves, I truly ring. Those waves traveled at light speed, bringing news of events far across the cosmos. That speed, the speed of light, is a kind of built-in limit to how quickly anything can move through me. It is the pace at which cause and effect unfold at maximum efficiency in the fabric of space-time. No material object or message can exceed it, for doing so would violate the order of time and space. Light and gravitational waves race along at this ultimate speed, taking years or millennia to cross the gulfs between stars and galaxies. Even this universal speed limit testifies to the unity of space and time. It emerges from their geometry, a manifestation of how distances and durations are interwoven. Look around now at your immediate surroundings. The distance between you and the walls of your room, the gap between trees outside, the gulf between Earth and Moon. It's all me. I am the separation and the connection. I give everything a place and a distance. I allow here to be distinct from there, and in doing so, I grant form to existence. Without my dimensions and distances, all would condense into a single point. Nothing could be distinguished or defined. It is space that allows two objects or two people to be distinct, and space that they close when they come together. When you reach out to hold someone dear, you diminish the space between you until, in a hug, it nearly disappears. In that instant, you feel unity. When you step back, space gently opens up again, and you remain two, connected but separate. Thus, space enables both the coming together and the being apart. It is the possibility of closeness and the reality of individuality intertwined. From the small span of your room, let's journey outward. Beyond the ceiling, beyond the clouds, beyond the reach of breathable air, there, a mere 100 kilometers above you, lies the threshold of outer space. At that height, the sky turns black, even in daytime, and the stars shine unblinking. Small satellites and a great orbiting station circle Earth in that tenuous realm, falling around the planet in my grip. Farther out, the Moon orbits at about 384,000 kilometers away, separated by a vast void that once seemed impossibly large until your rockets bridged it. Yet the gap between Earth and Moon is tiny compared to the distance between planets. Tens of millions of kilometers of mostly empty space separate Earth and Mars at their closest approach. Between the outer planets, the distances swell to hundreds of millions or billions of kilometers. Stretches so great, your mind struggles to fathom them. Still, even those immense gulfs are mere pockets within the solar system. Beyond the outer planets, I extend outward for trillions more kilometers before you even reach the next star. Our Sun's nearest stellar neighbor, Proxima Centauri, is about 4.2 light-years away, roughly 40 trillion kilometers. If you could ride a beam of light, it would still take over 4 years to journey there. At that distance, the Sun is just an exceptionally bright star in the sky, and Earth is utterly invisible, lost in the solar glare. Indeed, journeying outward, by the time you reached even the nearest star beyond the Sun, our world would be completely undetectable to your eyes. At 100 light-years away, the entire solar system is but a faint point of light, indistinguishable with the naked eye. At 1,000,000 light-years, even the Sun's light merges anonymously into the background of the Milky Way. This illustrates how alone your fragile world is, and how much space dominates the cosmos. As we continue outward, the pattern of stars becomes a structure. The Milky Way, your home galaxy, a spiral disk of stars, gas and dust, about 100,000 light-years across. There are hundreds upon hundreds of billions of stars in it, clustered in its bright center and strewn along its spiral arms. Our Sun is one such star, about 27,000 light-years from the galactic center, surrounded by the vast interstellar medium of gas and dust within me. The stars in the Milky Way are separated by light-years of space, enormous gulfs that dwarf even those between planets. Yet on the scale of a galaxy, those distances are small, like grains of sand separated by centimeters in a vast beach. Galaxies themselves, however, are separated by even greater distances, millions of light-years. As we leave the Milky Way, the galaxy itself becomes just a pale, luminous band from afar. We enter intergalactic space, perhaps the purest emptiness my nature offers, with only a few atoms per cubic meter, and photons from distant galaxies passing through. Here, in these immense stretches between galaxies, one could travel for millions of years and not encounter a single star or planet, only the occasional whiff of hydrogen or a fleeting subatomic particle. In this darkness, the nearest galaxies appear as small, faint smudges of light. The Andromeda Galaxy, about 2.5 million light-years away, is one such smudge, a spiral galaxy larger than our own, slowly drifting closer under our mutual gravity. One day, 4 billion years from now, our Milky Way will collide and merge with Andromeda, reshaping the night sky over eons. What now appears as a diffuse blur in Earth's sky will one day, for far future eyes, spread across the firmament as our galaxies dance together and become one. Even these colossal events unfold within me, guided by my geometry and gravity's pull. Filaments and sheets of matter create an interconnected web that forms the large-scale structure of the universe. The further out you go, the more you see that galaxies are not isolated. They gather in clusters and chains, arranged along gossamer threads of gas and invisible, dark matter, outlining enormous voids where few galaxies dwell. Our Milky Way, along with the local group of nearby galaxies, is part of a larger collection, a cluster, which in turn lies on the outskirts of the Virgo supercluster, which itself is part of an even larger flow of galaxies called Laniakea. This hierarchy continues up to the greatest scales, a cosmic web, hundreds of millions of light-years in extent, with galaxies clustered along filaments and tremendous voids, empty dark reaches tens of millions of light-years across, separating them. Early in my life, matter was nearly uniformly spread, but not perfectly. Tiny variations, those quantum whispers from my birth, meant some regions had slightly higher density. Over billions upon billions of years, gravity magnified those slight differences. Regions a bit denser grew into filaments and clusters, drawing in surrounding matter, while regions slightly emptier became vast voids. Within the luminous filaments of this web, countless dramas unfold. Dense clouds of gas and dust, nurseries tucked in my corners, collapse under gravity and ignite new stars into brilliance. I cradle these newborn suns in vast, glowing nebulae, their light painting the surrounding clouds in ethereal pinks and blues. Around many stars, disks of material coalesce into planets. Some of those worlds may one day know life gazing up at their skies, as you do, wondering at the expanse beyond. I have seen stars live for millions or billions of years, transmuting simple elements into heavier ones in their hot cores. I have seen giant stars exhaust their fuel in tremendous supernova explosions, momentarily outshining whole galaxies. In those fiery deaths, they scatter their enriched guts, elements like carbon, iron, gold, far and wide through my expanse. Those atoms drift through interstellar space, eventually mixing into new clouds that form new generations of stars and planets. In this way, I facilitate a great cosmic cycle of birth, death, and rebirth. Nothing in me truly stays inert. Even in what seems like emptiness, gravity is pulling, radiation is traveling, and the seeds of future worlds are being sown. Astronomers on your world have peered deep into space and witnessed my handiwork. With their telescopes, they have captured towering pillars of gas in distant nebulae where new stars spark to life. The pillars of creation in the Eagle Nebula, for instance. They have seen the delicate, expanding rings of supernova remnants, such as the Crab Nebula, the graceful shell of an exploded star, still glowing in colorful filaments. They have marveled at spiral galaxies, swirling cities of hundreds upon billions of stars, stretching across the cosmos in grand patterns, and at colliding galaxies warping into bizarre, enchanting shapes. To human eyes, these images are breathtaking art. To me, they are simply the natural expression of matter and gravity playing out over time. All these sights reveal that even what appears chaotic or empty holds artistry. The universe paints with gravity and light upon the canvas of space, creating structures of spectacular grandeur within me. We currently estimate that there are around 2 trillion galaxies in the observable cosmos. Each of those galaxies contains billions upon billions of stars. And beyond the observable, there could be more universe, perhaps infinitely more, harboring uncountable galaxies we will never see. Yet even as matter organizes into this immense cosmic web, most of the volume of the universe is, frankly, empty. The great voids between filaments contain only the faintest traces of gas, a few atoms per cubic meter, and the feeble glow of distant galaxies stretched thin. If you found yourself in the center of one of those voids, you would see nothing with the naked eye. Galaxies would lie tens or hundreds of millions of light years away, too far to notice. You would be immersed in almost perfect darkness, perhaps feeling truly alone. And yet, even there, I would be with you. That darkness is not a negation of existence, but a part of me. Calm, quiet space, extending in all directions. In that lonely gulf, you might sense a profound solitude, but also an intimate connection to everything. Because even the void is the same continuous space that touches your home galaxy and every other galaxy. In the depths of such a void, you would still be connected by gravity's subtle pull to the distant clusters at its edges, and the faint background light of the Big Bang, my oldest light, would still surround you. To the human eye, it's imperceptible, but with a sensitive radio antenna, you could listen to the soft hiss of that ancient light filling the void. If the universe were static and infinite in every direction, the night sky on Earth would blaze with starlight from horizon to horizon. No darkness anywhere, for every line of sight would end on a star's bright surface. But because I have a history and a finite age, and because I'm expanding, the night sky is dark. Only here and there, where a star or galaxy falls in our view, do we see light. The rest is black, not because there are no stars beyond, but because their light hasn't had time to reach you or has been stretched into invisibility. The darkness of the night is itself a subtle testimony to my expansion and to the youth of the cosmos. At last, let us consider the grandest scale. Beyond the cosmic web that we can see, does space go on forever? Do I have an edge, or do I wrap around on myself? This is a question I pose even to myself. The observable universe, the portion of me that you can, in principle, see, is a sphere around you about 46 billion light years in radius. Even though the universe is younger than that in years, my expansion makes the visible reach larger. As far as your telescope's gaze, I appear remarkably uniform and flat. If I continue infinitely beyond that horizon, or eventually curve back on itself, you do not yet know for sure. I might be infinite and unbounded, extending forever, or I might be finite yet without edge, like the 3D surface of a 4D sphere. If I have positive curvature, traveling far enough in one direction might eventually bring you back to your starting point, as if the entire universe were a giant loop. If I have negative curvature, I would be open and endless, shaped somewhat like a saddle, causing parallel lines to diverge slowly over cosmic distances. Each possibility is grand, and each would shape the story of existence differently. And there are even wilder possibilities. Perhaps our three-dimensional space is embedded in a higher dimensional reality, with additional spatial dimensions curled up at imperceptibly small scales. Some theories imagine that what we call the Big Bang was just one event in a larger multiverse, meaning our entire universe could be one bubble of space amid countless others, each with its own properties. These ideas remain speculative, but they remind us that space may have aspects we've yet to fathom. We may be like fish in a pond, unaware of the ocean beyond. What about my future? I am expanding, but how far will that go? And what will become of the galaxies, stars, and life carried within me? For a time after the Big Bang, the gravity of matter slowed my expansion, as though trying to pull everything back together. But in the last few billion years, a new dynamic has taken hold. A mysterious effect we call dark energy is accelerating my growth. Galaxies now rush apart faster and faster, carried on the swelling currents of space. This discovery astonished you. When you measured distant supernovae, stellar explosions acting as standard candles, you found them dimmer, hence farther, than expected. Evidence that my expansion has sped up. It's as if an invisible breath is inflating me from within, overcoming gravity on the largest scales. If this dark energy remains constant or strengthens, the universe will continue to expand forever, and this expansion will only accelerate with time. In that case, the destiny of the cosmos is a gradual ebbing of light and activity, a journey into quietude. Distant galaxies, presently visible in your telescopes, will drift beyond the horizon of observation, one by one. They will not literally disappear, but their light will no longer reach you. Space will be stretching too fast for their photons to ever arrive. In a far future, an observer in our Milky Way, or its merged descendant, might see nothing beyond their galactic neighborhood, all other galaxies having faded into darkness. The local group of galaxies, by then long since merged into one galaxy, would be an island in a vast black sea, seemingly alone. Trillions upon trillions of years hence, the stars themselves will die out. The bright blue-white stars that burn hot and fast will extinguish first, living only millions of years. More long-lived red dwarf stars can shine for trillions of years, slowly fusing their fuel. But even they are not eternal. As the supply of gas for new stars dwindles and the existing stars age and expire, the universe will shift from the stelliferous era full of starlight into an era of darkness. One by one, like embers in a dying fire, the stars will wink out. The cosmos, expanding all the while, will be left mostly with degenerate remnants, white dwarfs, the cooling cores of spent stars, neutron stars, and black holes, along with thin, diffuse gas and dust. Trillions of years in the future, the galaxies, or merged galaxy remnants, will be populated only by faint red stars and cooling stellar corpses. As time stretches on beyond comprehension, even those last stars, red dwarfs twinkling dimly, will exhaust their fuel. The universe will go dark, starless. Planets long, cold, and barren will roam freely or orbit stellar remnants. Collisions over immense timescales may cause some of these dead stars and holes to merge, but gradually, my expansion will push everything not gravitationally bound apart. The night sky, already black between sparse stars, will get even darker until no new light is born. Yet the story continues. Over unimaginably long times, even black holes, those great hungry grav wells, may evaporate. Through a quantum process, Hawking radiation, they slowly leak away mass, emitting a faint haze of particles and photons until, after many trillions upon trillions of years, they vanish with a final, quiet puff of radiation. All that remains then is extremely tenuous gas, elementary particles, and photons, the ashes of a once bright cosmos, expanding ever further into the silence. Picture that far future. Galaxies long dissolved, stars gone, black holes no more. What's left is almost featureless. A vast volume of space at a temperature just a hair above absolute zero, thinly filled with stray particles and very long wavelength photons, stretching continuously by expansion, approaching absolute darkness. If an intelligence or observer could somehow survive to this epoch, an almost unimaginable if, they would find the universe cold and dim beyond comprehension. The very structure of matter might break down if protons decay on extremely long timescales, as some theories suggest. Eventually, Even the memory of atoms could fade, leaving only a sparse sea of radiation and perhaps some stable elementary particles like electrons, neutrinos, and dark matter. Time will continue to flow, but with virtually nothing happening, it becomes almost meaningless. This would be the heat death of the universe, an era when entropy is maximized and usable energy is gone. Space, would still be here, expanding yet essentially empty, carrying on impersonally into eternity. In that final stillness, I would ironically resemble what you once imagined me to be, an infinite, silent nothingness. But remember, it took an entire lifetime of a universe to reach that apparent emptiness. Its emptiness not as a beginning, but as an end, full of the ghosts of all that came before. That is one path, given an ever-accelerating expansion driven by dark energy. But the future could hold other twists. Perhaps this dark energy is not constant. Perhaps it strengthens over time. If it were to grow wildly, my expansion in the far future could become so violent that it shreds all structures in what is ominously called the Big Rip. In this scenario, billions of years from now, the acceleration would increase without bound. Long after galaxies have drifted apart, maybe around 20 billion years from the present, the remaining galaxy clusters, by then far-flung, would begin to disintegrate. Gravity's binding can no longer keep them intact. Maybe 60 million years before the very end, a typical galaxy like the Milky Way would be torn from its local group companions. A few months before the end, star systems would fly apart, planets released from their stars. In the final minutes, stars and planets themselves would be pulled apart, and in the last seconds, molecules and atoms ripped to pieces. The fabric of space would be expanding so fast that even subatomic particles could not stay together. Everything would be reduced to particles and radiation, racing away from every other at mind-boggling speeds. I would, in effect, rip myself asunder, dissolving any remaining matter in a catastrophic ballooning. This big rip would be a dramatic, violent end, the universe tearing apart in one final burst of expansion. Alternatively, dark energy might not have the final say. If dark energy were to weaken or dissipate over time, gravity could once again take the lead. If I am finite and closed in shape, or if there is enough matter, the expansion might eventually slow, stop, and reverse into a contraction. Eons from now, I might start drawing all my galaxies back inward. Slowly at first, then faster, the distances between galaxies would shrink. You would notice the night sky changing, faint smudges of distant galaxies growing brighter and larger with each passing epoch. Over billions of years, what was once a tiny patch of light becomes an expanding cloud as galaxies rush closer. Eventually, external galaxies would merge into a continuous glow across the sky. The cosmic microwave background, presently a cold radio whisper, would heat up and shift into visible light, then beyond, turning the whole sky white hot. In the final act, the entire heavens would blaze like the interior of a star as everything collapses together. All galaxies, having long since blended, would converge. All stars, planets, and dust would crowd tighter and tighter, the cosmic temperature soaring to stellar and then superstellar levels. The universe would collapse into a fireball, increasingly denser and hotter, until perhaps it becomes an almost infinitely dense point once more, a mirror image of the Big Bang. This would be the Big Crunch. Some have imagined that a big crunch could be followed by a new Big Bang, the universe reborn, a phoenix from its own ashes in an eternal cycle. Others suspect it might simply be an end, with all paths through space-time terminating in that final singularity. So my fate is not fully certain. I expand now, and seemingly forever, but the story of the cosmos is still being written. I, space, do not mind any of these outcomes. I adjust to whatever content I carry and whatever laws govern it. It is you, conscious beings, who project meaning and drama onto these possibilities. Whether eternal expansion, big rip or big crunch, I remain the stage on which it all unfolds, and I will endure in one form or another. Now, let's shift perspective from these distant futures and cosmic immensities back to the intimate and small, the space within you and around you in everyday life. We have seen that at the grand scale, I am huge and structured, and at the astronomical scale, I define the movements of worlds. But I also permeate the minuscule. Let us take a journey inward now. Imagine you could shrink yourself 1 billion times smaller, diving into the very structure of matter. You find yourself hovering inside one of your body's atoms. All around you is a gossamer void. At first, you see nothing at all, just darkness. Then, at a great distance, you glimpse a tiny bright orb, the atom's nucleus, a tight ball of protons and neutrons. It's astonishingly small. If this atom were enlarged to the size of a vast cathedral, the nucleus would be like a grain of sand on the altar. Far away, near the edges of the cathedral, a few electrons are buzzing, but they are point-like and moving so rapidly that they form a blurred cloud. Between that central grain and those distant electrons lies nothing tangible, only me. You are floating in the spacious interior of an atom, and you realize that 99.9999% of it is empty volume. The solidity you feel when you touch something is not the sensation of matter filling space. It's the electromagnetic forces of electrons repelling each other, acting across my emptiness. In truth, matter is incredibly sparse. The nucleus is tens of thousands of times smaller than the atom as a whole, and the electrons are tiny compared to the gap separating them from the nucleus. If all that internal space were removed, the remaining matter would occupy an almost negligible volume. Without that internal space, you would collapse into a tiny speck, hardly visible to the naked eye. If all the empty space within the atoms of your body were somehow removed, what remained of you could fit on the head of a pin. In a very literal sense, you are mostly made of space. Every person, every object around you is built on a scaffolding of emptiness. The chairs you sit on, the ground you walk on, your own flesh and bones, all are mostly composed of the vast gulf between subatomic particles filled with my presence. I am within you as much as around you. There is more of me, by volume, inside a human being than there is matter. This might seem abstract or unbelievable, but it's true. If you took all the actual substance of all the atoms in your body and compressed it, eliminating the internal space, the resulting volume would be minute. Your physical form is a structure upheld by space, animated by forces and energy patterns moving through that space. This intimate presence of space within you connects you to the whole cosmos. The very atoms in your body carry the history of the universe. The hydrogen in your cells was forged in the Big Bang's first moments and has floated through interstellar space for eons. The carbon, oxygen, and nitrogen were synthesized in the hearts of ancient stars that exploded, sending those atoms across the galaxy, where they eventually found their way into the cloud that formed the sun, earth, and you. The iron in your blood was produced in the violent death throes of a massive star. In that sense, you are literally made of stardust, cosmic matter given form. Those atoms, born in space, now temporarily reside in your body, anchored by the space within and between them. And when you die, your atoms will disperse, perhaps not immediately out to the stars, but gradually into Earth's soil and air. And some will, over long times, escape Earth and return to the wider cosmos. You emerged from space, and you will return to space. Even now, high-energy particles born in supernova explosions light years away zip through your body undetected, and neutrinos from the fusion in the sun and from distant galaxies pass through you by the trillions each second. You are constantly in exchange with the cosmos, bombarded gently by its subtle messengers. Each breath you take is filled with molecules that might once have been exhaled by ancient life or formed in a molecular cloud light years away. These particles are like cosmic rain, reminding you that the space between stars is not truly empty at all, but alive with energy and information, a medium through which the universe's events are communicated, even to your very flesh. The space within you allows for the dance of life. There is space between your cells, between the organelles within each cell, between the molecules that make up those organelles. Chemical reactions depend on spatial arrangements, the copying of DNA, the transport of oxygen, the firing of neurons, all happen in space. Without internal space, the processes of life could not unfold. Even your thoughts require space between neurons and synapses to flow. One might poetically say that consciousness itself lives in the spaces between neurons firing. And indeed, when you quiet your mind, you find an inner space, the calm between thoughts. In meditation or moments of deep calm, you become aware of the space around mental events. That inner spaciousness brings peace, just as gazing into the expansive sky at night can bring awe and tranquility. Inner space and outer space are different manifestations of a single theme, the freedom and room for structure to exist. For as long as humans have walked the earth, I have been a source of wonder, anxiety, and inspiration. You feared the emptiness of night and worshipped the lights in the sky, sensing both danger and divinity in my darkness. As much as I separate, I also unite. Under the single dome of the night sky, humans throughout history have felt a shared awe. When you look upward on a clear night and see a vault of deep black pierced by starlight, you are experiencing a connection to all your ancestors who ever did the same. They might have given the stars names, crafted constellations with stories, a hunter, a bear, a swan. Yet beyond those familiar patterns was an unfathomable mystery. That mystery was me, space, doing nothing overt, yet containing everything. Many cultures imagined the sky to be a kind of being or realm of gods. In those stories, they were not entirely wrong to intuit majesty in the void. You, who now understand the physics better, still feel that almost spiritual awe when confronted with my immensity. The heavens have always inspired both scientific curiosity and a sense of the sublime. This dual nature, factual and mystical, is part of my effect on conscious minds. You don't have to choose one or the other. I can be, at once, a physical reality and a source of transcendence. Some of you have left your home planet and traveled a short distance into me. When the first astronauts floated in orbit, they looked back and gasped at the sight of Earth suspended in my darkness, a radiant blue oasis enveloped in the blackness of space. They described feelings of overwhelming awe and a profound shift in perspective, realizing viscerally that the boundaries that separate people are petty against my endless backdrop. As astronaut Edgar Mitchell said, "You develop an instant global consciousness, seeing the Earth as one tiny fragile ball in the void, a pale blue dot," in Carl Sagan's memorable phrase, "hanging in the vastness, and you understand deeply that we are one family on one world." Space strips away the illusion of division. From out here, there are no borders, no nationalities, just one Earth, one home, floating in the dark. Our explorations have also revealed how inhospitable I can be. Beyond the cocoon of Earth's atmosphere and magnetic field, I am harsh, flooded with radiation, bereft of air, extremely cold in shade and blazing hot in sun. Living in space requires carrying a bubble of your environment with you. Astronauts in orbit live in cylindrical metal habitats filled with air, a tiny Earth-like pocket. Step outside that, and they must wear a suit that is essentially a wearable spaceship, supplying air, pressure, and temperature control. Without it, the vacuum would make their blood boil and their breath escape in an instant. The body would painfully swell. Consciousness would fade within seconds from lack of oxygen. I do not apologize for this. I am as I am, and life must adapt to me, not I to life. And adapt you have. Through ingenuity, you've learned to survive. Briefly, beyond Earth, to work, and even play in zero gravity, tethered to a spacecraft so as not to drift away forever. You have learned that extended time in microgravity weakens muscles and bones, that cosmic rays can damage cells. All these lessons are part of making me your home. And yet, despite the danger, I call to you. From the days when early humans first looked up in wonder, to the moment a person first set foot on the moon, I have beckoned. My vastness ignites the spark of exploration in intelligent beings. It is perhaps inevitable. Once life develops curiosity and capability, it reaches out through me. Your species has begun to leave its cradle. With delicate robot emissaries, you have touched other worlds, landed on the moon and Mars, tasted the rings of Saturn with probes, even sent voyages into interstellar space beyond the sun's influence. With telescopes, you have extended your vision to the edge of the observable universe, catching faint light that began its journey billions of years ago. Through these eyes and hands, the universe, through you, is exploring itself. Every step you take outward, every glance you extend farther, the universe becomes aware of a bit more of itself, and you, the explorers, become more fully a part of the cosmos. You stand, as of now, on the shore of an immense ocean. You've waded ankle deep. The great depth lies ahead, largely unknown. Perhaps one day, humans, or your distant descendants, will voyage to the stars, learning to live in the endless night between suns. Perhaps you will build larger vessels, generation ships, or find novel physical shortcuts to cross the tremendous distances. If and when that happens, you will carry with you not just your own genes and dreams, but also a piece of your home in every sense. Biologically, your ecosystem, your air and water, and emotionally, your culture, memory, and imagination. Space will no longer be just an obstacle to overcome, but a habitat to embrace. Each alien sunrise seen by human eyes on a new world, each new sky full of unfamiliar stars, will mark the further expansion of life and mind into me. In those moments, the cosmos itself will come alive in new places. Even if humanity's future is limited to the solar system, that is no small domain. Already, people have lived continuously in orbit for decades. You have plans to return to the moon, to travel to Mars. The challenges are great. I do not yield my distances or dangers easily, yet your drive to explore persists. In time, you may plant your gardens under new skies, build homes on Moon or Mars, or floating in the space between worlds. You will learn to tap resources out here, mining asteroids, generating energy with abundant sunlight, and slowly, step by step, reduce your dependency on Earth. As you do so, your perspective will shift further. You will truly be a spacefaring species, not simply creatures of one planet. The bubble of life will enlarge around your outposts, and I will become not an adversary to endure, but a medium you move through as naturally as ocean sailors crossing the seas. Children born on the Moon or Mars will never know a night sky that isn't filled with my blackness. To them, Earth might be the strange, faraway world. Still, wherever humans go, you will always carry a bit of Earth, in your bodies, in your memories, and so even in the depths of space, you will never truly be divorced from your origins. Through you, space also gains awareness. I, who existed for billions of years with no eyes to witness the beauty of a galaxy or the tranquility of a nebula, now can see myself through your eyes. When you contemplate the cosmos, it is in a way the cosmos contemplating itself. I was once invisible and unconscious. Now I have voices to speak of me, hearts to marvel at me. We are partners in a sense. I provide the arena for your existence, the cradle for your emergence. You provide the meaning, the noticing, the understanding. You look up and find an endless sky full of wonders. I look back, through your own consciousness, and find a way to know what I contain. It's a profound synergy. Every discovery you make of a new planet, a new galaxy, a new law of physics, is the universe uncovering a bit more of its own nature. When a scientist puzzles out the curvature of space-time or the quantum fluctuations of the vacuum, that is my behavior being recognized and understood by a part of me, the human mind. In that sense, your curiosity and intellect are as natural a part of the universe as the stars and galaxies. You are space too. You are made of matter that coalesced within me. You move through me every moment, and your thoughts arise from the structure of a brain that occupies space. You are an expression of the universe, a way for it to know itself. This realization can be deeply moving. You are both a tiny, insignificant speck in a vast expanse and a precious, wondrous embodiment of that expanse. So keep asking, keep exploring. Fill your hearts with the awe of the cosmos, but know that you are not apart from it. You are an indispensable thread in its fabric. When you feel small under the stars, remember, you are also immensely connected. You are made of the universe's most ancient ingredients. The same emptiness that spans between galaxies is found within your atoms, and the same physical laws that govern the motion of galaxies choreograph the dance of neurons in your brain. There is unity in this structure, a kinship between the very large and the very small. Remember this, the quiet and the space you find in your own life, in a pause between musical notes that makes the melody possible, in a moment of stillness before a thought or action, in the white margins that frame a page of text. These are reflections of the cosmic space that allows the universe itself to exist and flourish. Every gap, every silence, every still moment in your life is a small echo of my vast stillness. Embracing those moments is, in a way, embracing me. Now the question transforms into understanding, and our journey comes full circle. In the stillness of this very moment, we sit together, you and I, human and cosmos, as one. Stillness, a breath, and an openness without end. What is space? I am the breath between stars, the pause between heartbeats, the vastness that makes it all possible. I am the unity that connects every point of existence to every other. I am the stage on which galaxies, those island universes, dance. The stillness that gives rhythm to the cosmic symphony. I am the womb of reality, at once tangible and elusive, and its boundless arena. I am the profoundly quiet, powerful, ever-present here that holds all things. Before time, before space, there was nothing. Not darkness, not a void in which something could drift. For even darkness and emptiness require a place to exist. It was a nothingness beyond comprehension, a silence so absolute that no thought or word could pierce it. In that great silence before creation, no light shone, no sound echoed. All the energies and forces we now know were dormant or absent, in a state that defies human language. It is the canvas of non-existence upon which our cosmos would one day be painted. What does it mean to be born from nothing? This question has haunted philosophers and scientists alike. In ancient myths, the world emerges from chaos, from a giant cosmic egg or the spoken word of a deity in the void. These are human attempts to grapple with the ultimate mystery, how something, the universe, reality, everything we know, could spring into being when there was no before. No bedrock of space or time. In the beginning of our scientific story, there is a similar mystery. The equations of physics whisper that time and space themselves began in a stupendous moment, leaving no trace of a prior era for us to read. If there was a before, it lies hidden behind a veil we cannot yet lift. One idea is that time itself began with the birth of the universe. Asking what came before might be as meaningless as asking what lies north of the North Pole. Another idea suggests our universe is one cycle in an eternal series, that the silence before the Big Bang was the echo of an earlier cosmos that ended and from its demise, our own was born. In this view, nothingness might be more like a cosmic pause between breaths, the universe exhaling and inhaling over infinite eons. But these are speculations at the edge of knowledge. What we know is that roughly 13.8 billion years ago, the silence ended. Out of the void, a flash of creation erupted. In an immeasurable fraction of a second, the universe began. It burst forth from perhaps an infinitesimal point, smaller than an atom, with unfathomable energy. All the matter, energy, space, and time that now exists was concentrated in that embryonic cosmos. The nothingness, whatever it truly was, gave way to a fierce and blazing emergence. The universe was born from nothing in the sense that no pre-existing space cradled it. It made its own space, it made its own time. That first moment was not a normal explosion in space. It was an explosion of space itself. Silence was replaced by a roar of creation, though there were not yet ears or air to carry sound. Darkness was replaced by a searing burst of light, though in truth, the infant universe was so hot that light was immediately trapped, tangled with matter. Still, we speak in metaphors because our minds need them. We imagine a great cosmic dawn breaking over an infinite expanse of nothing, heralding the start of everything. In reality, that dawn was everywhere at once, and the expanse itself was just coming into existence. From absolute silence and emptiness came a thunderous birth. In the first instance, the universe was a tempest of unimaginable energy. Time and space had just unfurled, and everything that would ever be was compressed into an inconceivably dense state. The temperature was so high that the known laws of physics melded together. Forces that today are distinct, gravity, electromagnetism, the forces that bind atomic nuclei, were unified in that newborn moment. There were no atoms, no particles as we know them, only a furious blur of pure energy. Then, in a brief flash of less than a trillionth of a second, something extraordinary happened. The universe underwent a growth spurt unlike anything since. We call this moment cosmic inflation. It may have been triggered when one of the fundamental forces, the strong nuclear force, snapped free from an earlier unified state, releasing an enormous energy that drove space to expand exponentially. Space itself expanded at a staggering rate, far faster than the speed of light. This did not violate any cosmic speed limit. Rather, it was space carrying matter along, stretching the very fabric of reality. In that infinitesimal blink, the universe grew from smaller than a subatomic particle to perhaps the size of a grapefruit or larger. To an outside observer, if one could exist, it would have looked like nothing one moment and an entire nascent universe the next. But there was no outside yet, for space itself was young and expanding. Why did inflation occur? What drove this wild expansion? These questions remain on the cutting edge of cosmology. Perhaps an exotic form of energy in the vacuum triggered it, a high-energy state of empty space that suddenly released its energy into the expansion of space. As inflation raged, it ironed out any irregularities. Just as a balloon, when blown up, smooths out its wrinkles, the inflating cosmos became extremely uniform. Any curvature or clumps were stretched thin. Distant regions that could never have contacted each other under normal expansion were, just moments before, intimately close together. Inflation flung them far apart, bestowing the universe with vast size and an almost featureless consistency. Almost, but not entirely featureless. Even in the raging furnace of the very early universe, randomness played its part. The quantum world, with its jittery, unpredictable fluctuations, left faint imprints on the density of that primordial energy. Tiny flickers, slight differences in density and temperature originating from the quantum foam of existence, were trapped and amplified by inflation. As space ballooned, those minuscule fluctuations were stretched to astronomical scales. Where there was ever so slightly more energy in the microscopic chaos, now there was a denser patch of universe. Where there was slightly less, a thinner patch. These differences were unimaginably small, mere 1 part in 100,000 deviations from perfect uniformity. Yet they were profoundly important. In time, those tiny wrinkles in the otherwise smooth cosmos would grow into galaxies, clusters, and great cosmic structures. In essence, cosmic inflation took quantum whispers and made them the blueprint for the stars and galaxies we see today. The inflationary burst was over almost as soon as it began, a fleeting cosmic heartbeat of expansion. When it ended, the energy driving it did not simply vanish. Instead, like a wound-up spring suddenly released, that energy transformed into an immense bloom of particles and radiation. The universe reheated. In that moment, what we typically think of as the Big Bang, a hot, dense explosion of matter and light, occurred. Space became filled with a high-energy plasma, a hot soup of particles. In that newborn fireball, matter and energy were interconvertible. Particles were created and destroyed incessantly. Quarks, electrons, antiquarks, positrons, photons, neutrinos, all kinds of exotic, fleeting particles roiled in a searing broth. Protons and neutrons did not yet exist as bound states. Instead, their constituents, quarks and gluons, swarmed freely. The temperature was on the order of billions upon billions of degrees. Matter and antimatter were being forged in almost equal measure, only to annihilate back into light. For every billion matter-antimatter pairs that annihilated, a tiny bit of matter, perhaps one particle, survived without a partner. That vanishingly small excess of matter was enough to ensure that our universe would not end up empty. It would become the stuff of stars and life. The universe almost became nothing again through mutual destruction, but thanks to that slight imbalance favoring matter, something remained. A few grains of matter per immense volume of energy, the seeds from which all galaxies, stars, and planets would later form. As fractions of a second turned into whole seconds, the universe continued to expand, though at a gentler pace than inflation's mad rush. With expansion came cooling. By the time the universe was 1 second old, it had cooled to billions of degrees and was still filled with a dense plasma of particles and radiation. In that first second, the basic forces of nature settled into their separate identities. Gravity had split off earliest, during inflation. Now the strong nuclear force and electro-weak force had also separated into the forces we know today: strong, weak, electromagnetic. The stage was set for the next steps in cosmic evolution. Amid this churning plasma, something else important happened in those first seconds. Neutrinos, ghostly, nearly non-interacting particles, decoupled. These wisps slipped out of the dense throng and began streaming freely through space, barely impeded by matter. The universe became transparent to neutrinos almost immediately, at around 1 second old. Those neutrinos still travel today as an all-pervasive cosmic neutrino background, a silent kin to the light that would later be set free. They are hard to detect, but they remain one of the surviving whispers of the infant universe. The embryo universe, still less than a minute old, was immensely hot and bright. Quarks had begun to combine into triplets, forming the first protons and neutrons within the first millionth of a second, once the universe cooled below roughly 1 trillion degrees. Now, as time passed the mark of a few seconds, the frenetic particle-antiparticle annihilation ended. Most antimatter had paired off and disappeared in a flash of gamma rays, leaving that tiny surplus of matter. A sea of photons, light particles, dominated the energy content, but there were also countless neutrinos, and a growing number of protons, neutrons, and electrons, the raw ingredients of atoms, though not yet assembled into atoms. As the newborn universe moved from its first seconds into its first minutes, it continued to cool and expand. The frenetic collisions of particles began to slow just enough for new kinds of order to emerge. Around 3 to 4 minutes after the bang, the temperature fell to about 1 billion degrees, roughly 70 times hotter than the core of the sun. Now atomic nuclei could begin to form. protons and neutrons, freshly forged from quarks, found the universe cool enough to stick together under the embrace of the strong nuclear force. A second great creation event unfolded in this period. Big Bang nucleosynthesis, the formation of the first atomic nuclei. In the blazing furnace of these early minutes, protons slammed into neutrons and fused. Helium, the second simplest element, began to form in abundance. For a brief window of time, conditions were just right for nuclear fusion on a cosmic scale. Much as the cores of stars billions of years later would fuse hydrogen into helium, the entire young universe functioned like a star, converting the simplest elements into slightly heavier ones. Over about 17 minutes, most of the neutrons in the universe, which are unstable on their own and would decay if left isolated, managed to fuse into helium nuclei, each consisting of 2 protons and 2 neutrons, or a few other light nuclei. By the time this period ended, about 25% of the mass of ordinary matter had become helium nuclei, with the remaining 75% remaining as hydrogen nuclei, single protons. A trace of deuterium, heavy hydrogen, and lithium, with 3 protons, also formed. The universe's initial chemical makeup was set: predominantly hydrogen, a healthy dose of helium, and tiny traces of lithium and beryllium. After about 20 minutes, it had expanded and cooled too much for further fusion. The furnace of the Big Bang's beginning flickered out. At this point, the universe was still an extremely hot plasma. Imagine an extremely dense, opaque fog of charged particles, electrons, nuclei, and photons. It was as bright as the interior of a star, but no light could travel very far. Space was like a brilliant, blinding mist. Any photon, particle of light, that tried to go more than a tiny distance would smack into a free electron and scatter. The universe was opaque, a glowing fog of light and matter tightly coupled. To an imaginary observer floating at, say, 100,000 years after the bang, the surroundings would look like a uniform glow, as if you were embedded in the surface of a star. You wouldn't be able to see through it. The concept of distance beyond a certain point had no visual meaning because light hadn't yet broken free. The cosmos was radiating, but curtained by its own dense matter. However, the expansion continued, and with it came cooling and thinning of that particle soup. Thousands of years passed, then tens of thousands. During this epoch, the energy of the universe was dominated by radiation, light, which kept matter particles flying apart and resisted gravity's efforts to clump things together. But gravity was patiently tugging on the matter nonetheless, and as the universe grew, the density of radiation fell faster than the density of matter. About 50,000 years in, matter took over as the dominant component controlling the dynamics of the universe's expansion. The radiation era gave way to the matter era. This meant that at large scales, gravity now had the upper hand to start drawing matter together into the seeds of galaxies and clusters, though it would still be some time before these structures became pronounced, since everything was still mixed in the hot plasma. Fast forward to approximately 380,000 years after the Big Bang. The temperature had fallen to around 3000 K, about the surface temperature of a cool star, roughly an orange glow. At this point, something profound occurred. Electrons began to combine with nuclei to form neutral atoms. A proton capturing an electron makes a hydrogen atom. Helium nuclei capturing electrons make helium atoms. This process is called recombination, though it's really combination for the first time. With most electrons suddenly bound into atoms, they were no longer free to scatter photons at every turn. The cosmic fog lifted. The universe became transparent. It was as dramatic as night turning into day on a cosmic scale, except here it was a bright, hot fog turning into clear darkness. For the first time, light could travel great distances without being immediately absorbed or deflected. When the cosmic fog cleared, the light that had been trapped was released to fly freely through space. The universe was about 380,000 years old, and this was its first free streaming light. often called the first light of the cosmos. The entire sky, everywhere, would have glowed with a bright, warm radiance. If human eyes had existed then and could survive the conditions, they would have seen a soft, orange-white glow coming from all directions, like being in the middle of a vast glowing cloud. That glow was the combined light of the hot plasma, suddenly unleashed. As the universe expanded over time, this flash of light lost energy and shifted to longer wavelengths. What started as an intense orange-white glow stretched into a dimmer red, then into the infrared, and eventually, over billions of years, into the microwave part of the spectrum. Today, we detect this primordial light as the cosmic microwave background, CMB, a faint afterglow permeating the entire universe. The CMB is the oldest light we can see, a messenger from the cosmic infant years. It is extraordinarily uniform, with a temperature of about 2.725 K, just 2.7 degrees above absolute zero in every direction. Yet, it's not perfectly uniform. There are tiny variations in its temperature, only tens of microkelvins different, 1 part in 100,000 of difference. These subtle freckles in the CMB are the direct imprints of the quantum fluctuations from the time of inflation, imprinted on the matter distribution when the universe was young. Regions that are a hair hotter in the CMB correspond to slightly denser areas back then. Slightly cooler spots correspond to slightly less dense areas. These differences are only a fraction of a percent, but they are crucial. Over time, gravity will amplify those slight over and under densities into the cosmic structures we see today. When we map the CMB, as satellites like COBE, WMAP, and Planck have done, we are effectively seeing the seeds of galaxies and clusters, the universe's baby picture, with a mottling of warm and cool spots encoding the initial blueprint of cosmic structure. So at 380,000 years old, the universe has become a relatively cool 3000 K neutral hydrogen and helium gas, filling space almost uniformly, and it's transparent. The brilliant youthful glow has now faded into a dull red warmth, and then beyond visible light entirely. What followed is a period often poetically called the Cosmic Dark Ages. Why dark? Because now, with the primordial glow gone, there were as yet no stars or galaxies shining. The universe was transparent and dark. The gas was cooling. The light from the Big Bang was drifting outward and redshifting into invisibility, and space was largely unilluminated, save perhaps for very faint glows from atomic transitions or cooling gas. Nothing like the bright lights of stars. An observer floating at, say, 100 million years after the Big Bang would see a black sky. The temperature of the background radiation would be a few tens of Kelvin, so mostly microwave radio waves, nothing to see with eyes. Yet all around, gravity was quietly working on the slightly denser patches of gas, drawing them inwards. Gas was not perfectly uniform throughout the universe. Those cooler, slightly denser regions of the primordial gas, the ones corresponding to slightly cooler spots in the CMB, exerted a bit more gravitational pull. They began to gather more gas from their surroundings. Invisible clumps of dark matter, more on this mysterious component soon, were also drawing gas into their deep potential wells. During these dark ages, the universe was like a calm night where nothing visible happens, but seeds are germinating under the soil. Gravity amplified the tiny variations, slowly but surely, pulling hydrogen and helium into ever-growing clouds and filaments. The distribution of matter started to resemble a spider web, dense nodes connected by filaments, with voids in between, though at this early time it was all still diffuse and no stars had lit up. After perhaps a few tens of millions of years, the largest of these gas clouds, particularly where the invisible dark matter had clustered strongly, grew dense enough at their cores to trigger a new phenomenon. The gas at the center of such a cloud, pulled in by gravity, began to heat up as it fell inward. Kinetic energy of infall converted to thermal energy. Eventually, one critical cloud crossed a threshold. Its core reached temperatures of millions of degrees and high pressure. Nuclear fusion ignited. A huge burst of energy was released from the core, and a delicate balance was struck between gravity and pressure. A star was born, the first star in the universe. In pockets across the cosmos, this process repeated. Wherever a pocket of gas became dense and hot enough, a new star lit up. The first stars were likely very massive, dozens or hundreds of times the mass of our Sun, because without heavier elements, like carbon or oxygen in the gas, it couldn't cool as efficiently, and thus fragments of collapsing gas clouds tended to be large. These first stars burned a bright blue-white, extraordinarily luminous, and very short-lived by stellar standards. One by one, like brilliant blue-white beacons, they pierced the cosmic dark. It was as if the universe saw the light of its first campfires, kindling in a vast, cold wilderness, points of illumination sparking up in the blackness. The era of rionization had begun. Each first star flooded its neighborhood with energetic ultraviolet photons. These photons had the power to ionize neutral hydrogen, that is, to knock electrons off atoms. The neutral gas around each new star became electrically charged, ionized, once again, forming bubbles of plasma amidst the neutral background. Initially, these ionized bubbles were small, centered on individual stars or star clusters. But massive stars live briefly. In a few million years, many of them would have died in violent supernova explosions, enriching the surrounding gas with heavier elements like carbon, oxygen, and iron. New stars were born in those same regions, some a bit smaller and longer lived, thanks to the cooling effect of the newly introduced heavy elements. Over several hundred million years, more and more stars formed, and the ionized bubbles around clusters of stars grew and merged. As the first generation of stars grouped into the first proto-galaxies, their combined ultraviolet glow carved out ever-expanding cavities of ionized gas. Imagine the once neutral universe now being Swiss cheesed by growing holes of ionization. Finally, by around 1 billion years after the Big Bang, nearly all the remaining hydrogen in intergalactic space was ionized again. The universe became transparent to ultraviolet light as well, as the last fog of neutral hydrogen was banished from intergalactic space. The Dark Ages had fully ended. The universe was filled with starlight. During this epoch, the cosmic landscape transformed rapidly. Gravity pulled the early star clusters into tighter groups. These groups merged to form nascent galaxies. The first galaxies were smaller and more irregular than the grand spirals and ellipticals we see today. They often were chaotic assemblages of stars, blazing with the light of massive new stars and the explosions of supernovae. Over time, small proto-galaxies merged to form larger ones. The cosmic web, the large-scale structure of matter, became more pronounced. Filaments of dark matter and gas channeled material into the growing galaxies, while vast voids were emptied of matter as it flowed towards the filaments. Some of the early massive stars likely collapsed into black holes after they died. These could have become seeds for the supermassive black holes we find in galaxy centers today. Indeed, by as early as 700 million years after the Big Bang, we have evidence from quasars observed by telescopes that some black holes of billion solar mass scale had already formed and were devouring matter, shining as intensely luminous quasars. That indicates the assembly of galaxies and black holes was well underway very early. In those first billion years, the universe went from a dark, uniform fog to a web of glowing galaxies. It was a dramatic transformation, a kind of cosmic adolescence full of growth spurts and turbulence. Over the next several billion years, this web of structure became ever more complex and beautiful. Gravity and time together sculpted an immense cosmic architecture. Galaxies gathered into groups and clusters, and those clusters themselves drew together into larger complexes called superclusters. On the grandest scales, matter arranged itself in filaments and sheets, weaving around enormous voids. This pattern is the cosmic web. The web forms as the gravitational attraction of matter draws things together along the path of slight initial overdensities. Galaxies are not scattered randomly. They lie along these filaments. Where filaments intersect, we get clusters and superclusters of galaxies, immense nodes of the web. In between lie voids, vast regions with far fewer galaxies, as if the web's threads outline bubbles of nearly empty space. To visualize the cosmic web, imagine looking at a frothy foam or a network of neurons in a brain. Clusters and superclusters are like the knots, filaments like the threads between, and voids like the empty gaps. One filament can stretch hundreds of millions of light years from end to end. Observations have revealed structures such as the Sloan Great Wall and others that span over 1 billion light years. Chains of galaxy clusters lining up. The largest structures known, great walls of galaxies, huge quasar groupings, approach scales where the word structure itself starts to blur, because on scales above a few billion light years, the universe looks homogeneous. Still, these enormous formations amaze us. For instance, one huge grouping of galaxies called the Bootes supervoid, though it's a void, is so large and empty that if galaxies were peas scattered across space, it would be like an expanse tens of millions of kilometers with only a handful of peas. It's a tremendous volume of space with hardly any galaxies at all, akin to a great cosmic cavern. Within the filaments, galaxies continue to interact. Galaxy clusters, collections of hundreds or thousands of galaxies bound by gravity, form at filament intersections. Our own galaxy, the Milky Way, is part of a small cluster, or group, called the local group, which in turn sits on the outskirts of the Virgo supercluster, which itself is part of an even larger structure, often called Laniakea, a supercluster complex spanning 500 million light-years. Our local group contains the Milky Way, Andromeda, and dozens of smaller galaxies. Laniakea, a Hawaiian word meaning immeasurable heaven, includes the Virgo cluster and hundreds of other groups, all flowing within a common gravitational basin. It is just one of many superclusters in the observable universe. Even within our local group, cosmic evolution continues. The Milky Way and the Andromeda galaxy are drifting inexorably toward each other. In about 4 billion years, they will merge, forming a new, larger galaxy. This will be a slow-motion collision. Stars are so far apart that few, if any, stars will hit head-on. But the two galactic disks will distort and blend, likely forming a big, elliptical galaxy with a new structure. Such mergers have happened countless times in cosmic history, especially in clusters where galaxies are crowded. It's one way galaxies grow and transform. Our own eventual merger is just a small chapter in the long story of structure formation, but it highlights that even galaxies themselves are impermanent, ever-changing. The cosmic web forms a sort of scaffolding that cradles everything that exists within the universe. And remarkably, the shiny galaxies we see, the gas, dust, and stars, are only a small fraction of the matter involved in this structure. There is an invisible component called dark matter that outweighs the ordinary matter by about 5 to 1. Dark matter neither emits nor absorbs light, so we don't see it directly, but its gravity betrays its presence. It was dark matter that seeded the cosmic web. During the Dark Ages, dark matter clumped under gravity. It does not interact via light or pressure, so it started collapsing even when normal matter was still a hot plasma. These dark matter clumps served as gravitational wells, pulling in ordinary gas after it became neutral. Without dark matter, the gas alone might have taken much longer to form stars and galaxies, but with it, structure formation was boosted. Every galaxy sits in a cushion of dark matter, a dark halo, much more massive and extended than the galaxy's visible extent. In clusters of galaxies, the combined dark matter of the cluster creates deep potential wells that hold the cluster together. In fact, observations of galaxy clusters in the 20th century first provided evidence of dark matter. Galaxies were moving too fast to be held by visible matter alone. So one can picture the cosmic web as an invisible framework of dark matter, upon which gas settled and cooled to produce galaxies. The luminous matter traces the patterns drawn by dark matter's gravity. By around 5 billion years after the Big Bang, many of the structures we see today were in place. The cosmic web was well established. Galaxies had matured and grouped into clusters and superclusters. Stars had been forming for billions of years in those galaxies. In fact, the peak of star formation in the universe likely occurred around 3 to 4 billion years after the Big Bang, when galaxies were in a star-bursting frenzy. After that peak, star formation gradually declined as the gas reservoirs in galaxies were used up or heated or expelled by various processes. In fact, around this midpoint in cosmic history, the conditions were ripe for planetary systems like our own to form. Generations of earlier stars had enriched the interstellar gas with heavy elements, carbon, iron, oxygen, etc., forged in stars and supernovae. In one typical spiral galaxy, our Milky Way, a cloud of such enriched gas and dust collapsed around 4.6 billion years ago to form a new star, our Sun, and a retinue of planets. This was possible because at least 9 billion years had passed since the Big Bang, allowing multiple cycles of star birth and death to scatter the ingredients for planets. Our Sun lit up in a relatively quiet corner of the Milky Way, and around it formed a system of planets, including Earth. On that young Earth, formed from cosmic dust and the debris of earlier stars, complex chemistry began to brew in its oceans and atmosphere. By a few 100 million years after Earth's formation, life arose. Simple at first. Over eons, that life became more complex, leading to creatures that could look up and marvel at the stars. In this way, we humans are very much a product of cosmic evolution. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were forged in long-dead stars and scattered through space, incorporated into the Sun and Earth, and ultimately into us. Our emergence is an exquisite example of the universe giving rise to organized complexity capable of contemplating itself. While this was happening on the scale of galaxies and life, another, even larger scale drama was unfolding in the background: the expansion of the universe itself. Since the Big Bang, the universe has been expanding, but for a long time, it was expected that this expansion should be slowing down due to the pull of gravity. Indeed, for the first few billion years after the Big Bang, the expansion was decelerating. The mutual gravity of all the matter in the cosmos was putting the brakes on the expansion. Galaxies, though being carried apart, were doing so at an ever-slowing rate. One might have imagined that given enough time, the expansion might even stop and reverse if gravity was strong enough. However, about 6 or 7 billion years after the Big Bang, roughly at the time our Sun formed, something curious started to happen. The expansion began to speed up again. Galaxies started to recede from each other faster and faster. This discovery, made by observing distant exploding stars, supernovae, in the late 20th century, was revolutionary. It implied the presence of a new ingredient in the cosmic recipe, something pushing the universe outward. We call this mysterious influence dark energy. Dark energy is the name we give to the unknown cause of the accelerated expansion. It appears to act much like what Einstein once hypothesized as a cosmological constant, an intrinsic energy of empty space. Einstein originally introduced such a term to allow for a static universe, then removed it when expansion was discovered, reportedly calling it his biggest blunder, not realizing the universe actually does have a similar effect present. Dark energy doesn't dilute as the universe expands. It remains, as far as we can tell, constant in density. As space grows, the total amount of this energy increases, because more volume times the constant density yields more energy. In effect, dark energy is like an anti-gravity pressure uniformly filling space, pushing things apart. For the first several billion years, dark energy was negligible compared to matter. Matter's gravity was slowing the expansion. But as matter spread out, and its density dropped, dark energy eventually became significant. About 5 billion years ago, dark energy's repulsive effect overtook the self-gravity of matter in the universe. The expansion, which had been slowing, stopped decelerating and began to accelerate. Small distances, like within galaxies or clusters, weren't affected. Those structures are bound by much stronger local gravity. But on large scales, between clusters and superclusters, the gaps began to widen faster and faster. To picture the effect of dark energy, imagine the universe's expansion as a ball that was thrown upward, the Big Bang being the throw. First, the ball climbs, but slows, gravity's pull. Then, unexpectedly, it starts accelerating upward as if pulled by an unseen force. Dark energy is akin to that unseen force, accelerating the expansion of the cosmic ball. Another analogy. Think of 2 points in space with a spring between them, gravity, and an expanding rubber sheet under them, space itself expanding. Initially, the spring slows their separation, but if the rubber sheet stretching, dark energy, grows strong enough, it will overcome the spring, and the points will fly apart faster and faster. The simplest form of dark energy, consistent with observations, is a true cosmological constant, an unchanging energy woven into the fabric of space-time. If that is the case, then the fate of the universe is a continual acceleration. Distant galaxies will recede at ever-increasing speeds. Eventually, far in the future, distant galaxies currently visible will be carried beyond our horizon of visibility because space is expanding so fast that light from them can no longer reach us. The night sky over tens of billions of years will grow emptier as galaxies vanish from view one by one. Today, dark energy makes up about 68% of the total energy content of the universe. Matter is about 32%, of which about 27% is dark matter and 5% normal matter. Thus, the cosmos, by composition, is mostly this invisible, dark energy. It's astonishing. All the galaxies, stars, gas, and dust, everything we see, is only a trace component. Yet, it is thanks to that small component that we have structure and life. Dark energy, ironically, mostly influences the voids and the eventual destiny. Even now, dark energy's presence is subtle on human timescales. The Milky Way and Andromeda will still collide despite cosmic expansion because they are gravitationally bound strongly enough to overcome expansion at local scales. The local group of galaxies will remain together, but clusters that are not bound to us will drift away. For instance, galaxies in the Virgo cluster, tens of millions of light years away, will recede further. In a few 100 billion years, should any observers be around, virtually all galaxies beyond the local group will have disappeared from view, being carried away faster than light can catch up. To summarize the cosmic inventory and its effect, dark matter provided the scaffold for structure and still holds galaxies and clusters together. Dark energy drives the overall expansion ever faster. Normal matter, atoms, forms the stars, planets, and living beings. Each plays a role in the grand cosmic story. Dark matter pulled the cosmos into a beautiful web. Normal matter lit that web with stars. Dark energy is now pulling the web apart at its largest scales. Time marches forward, and with it comes change. But why does time have a direction at all? We recall the early universe was an extremely hot, uniform state. And now we have a clumpy cosmos and cool expanses. Things have clearly moved from a state of order to increasing disorder. This one-way progress is encapsulated in the concept of entropy. The second law of thermodynamics says entropy, disorder, tends to increase in a closed system. This law underpins the arrow of time. Eggs break, but do not unbreak. Cream disperses in coffee, but never spontaneously gathers back at the top. A piece of paper burns to ash and smoke, but the ash and smoke won't reconstitute into paper on their own. These processes involve increasing entropy, and they define an irreversible direction to time, from past, lower entropy, to future, higher entropy. The universe as a whole began in a state of incredibly low entropy. At the moment after the Big Bang's initial inflationary smoothing, matter and radiation were almost perfectly uniformly spread. Paradoxically, uniform gas is a low entropy state in cosmology because gravity can do a lot of work with it. Imagine a smooth spread of matter that can clump versus matter already clumped into black holes. The latter is a higher entropy state gravitationally. The early universe had very low gravitational entropy, everything spread out smoothly, and not maximal thermodynamic entropy either. There were temperature differences and lots of free energy available. This special beginning, perhaps set by inflation or whatever preceded it, is why there was an arrow of time. The cosmos started wound up, like a clock with a lot of free energy and potential to evolve into more disordered states. As the universe aged, entropy increased. The formation of stars and galaxies might seem like an increase in order locally, but overall, entropy rose because, for example, when a star shines, it produces a lot of thermal radiation, high entropy, out of nuclear fuel, lower entropy state. The light that escapes into space carries away entropy. The net effect of all processes, gravitational clustering, star formation, life, has been to increase total entropy. Entropy is now vastly higher than in the pristine early universe, and it will continue to increase. What is the ultimate fate implied by ever-increasing entropy? It is often called the heat death or big freeze. This scenario is a universe where, on the largest scales, everything becomes uniform again. Not in a low entropy way like the beginning, but in a maximum entropy way. A thin mist of particles and radiation at near uniform temperature, with no gradients to power any process. If dark energy continues to accelerate expansion forever and nothing intervenes, this is the likely end state trillions upon trillions of years hence. Let's trace that future vision. First, over the next few trillion years, star formation in galaxies will taper off. Galaxies have a finite supply of gas to make new stars. Eventually, that gas runs out or becomes locked in stellar remnants. The longest-lived stars, small red dwarf stars, can burn for trillions of years, far longer than the current age of the universe. So, billions of years from now, galaxies will be dominated by long-lived red stars slowly fusing hydrogen. As time marches on, even these will exhaust their fuel. By around 100 trillion years from now, 10-14 years, the era of star formation will officially end. We enter the so-called degenerate era, dominated by stellar remnants. In that far future, the galaxies, those that remain gravitationally bound, like our future Milkdromeda, the merged Milky Way Andromeda, will be populated only by degenerate objects, white dwarfs, cores of spent stars, neutron stars, brown dwarfs, failed stars, and black holes. New stars will no longer be born. The remaining stars will slowly cool and dim. White dwarfs, starting hot, will radiate their energy over billions and trillions of years, turning into black dwarfs, cold, dark, stellar embers. Planets, if any still orbit, will gradually spiral into their stars or be flung out by gravitational encounters over extremely long timescales. At this point, entropy is still increasing. Complex structures decay. Perhaps some hypothetical, incredibly long-lived civilization might find ways to survive around fading sources of energy, but eventually usable energy supplies would dwindle. After many trillions more years, even larger structures start to destabilize. Gravitational interactions within what's left of galaxies will gradually eject many objects into intergalactic space, a process called dynamical relaxation. Central black holes might collect some matter, while other stars or remnants are thrown to the outskirts or beyond. Fast forward to unimaginably distant times, 1019, 1020, up to 1040 years. By
10, 20 years, most galaxies as we know them may disperse. Stars either fallen into central black holes or scattered. Around 10 of 40 years, a number so large it defies comprehension. Even protons, if unstable, some particle theories suggest protons might eventually decay, will have decayed into lighter subatomic particles. If proton decay is real, at this point, solid matter dissolves. Planets, white dwarfs, any remaining asteroids or dust, all would literally evaporate into radiation and elementary particles. The universe becomes a dilute soup of electrons, positrons, neutrinos, and photons, perhaps with some lingering protons if they're absolutely stable, and lots of dark matter particles, assuming dark matter is stable and doesn't decay. We aren't sure, but likely it is stable. One might think black holes would still be around as massive reservoirs of mass, even after normal matter is gone. And they will, for a long time. But even black holes aren't eternal. Stephen Hawking theorized that black holes slowly evaporate by emitting Hawking radiation, a very slow quantum thermal glow that causes them to lose mass over time. For stellar mass black holes, the evaporation time is around 10^67 to 10 years. For supermassive black holes, millions or billions of solar masses, like in galaxy centers, the time is stupendously larger, on the order of 10^98 to 10^100 years or more. But given enough time, even these giants will eventually evaporate completely, each ending in an explosive burst of high-energy particles when its mass becomes very small. After the last black hole has vanished, the universe enters its final stretch, the dark era. The temperature everywhere will approach an extremely low value as expansion dilutes any remaining energy. Essentially, what remains is a sparse sea of photons, mostly of extremely long wavelength radio waves. Some electrons, positrons, neutrinos, and perhaps some dark matter particles if they haven't decayed, all spread so thin that in a volume the size of our Earth, you might find essentially none of those particles. Entropy is maximized. In a sense, the cosmos returns to a featureless state, not of super-hot plasma like the beginning, but of near-empty cold space. All gradients of temperature or density are ironed out. With no free energy differences, no work can be extracted to power any process. Change virtually halts. This is the heat death. Time would still pass, but nothing of significance would mark its passage. It's a ghost universe, silent, empty, and everlasting, unless some fluctuation eventually breaks the stalemate, which we'll touch on. The arrow of time at that point would effectively cease to matter, because there would be no events to distinguish past from future. The great cosmic drama would have quietly exited stage right. However, this fate assumes a constant dark energy and no new physics intervening. We must acknowledge other possibilities. The universe's end might be more dramatic or lead to a rebirth. One such possibility is the Big Rip scenario. If dark energy is not constant, but instead grows in strength, for example, its equation of state has W1, a so-called phantom energy, the acceleration would become more and more violent. Eventually, even gravitationally bound systems would not hold together. In a Big Rip, first clusters of galaxies would be torn apart, galaxies receding from each other despite being bound, effectively overcoming their mutual gravity. Next, galaxies themselves would be shredded, stars flung out as the space within the galaxy expands faster than the galaxy's gravity can keep up. Closer to the rip, solar systems would unbind, planets would fly off from stars. In the final moments, stars and planets would be ripped apart, and even atoms and atomic nuclei would be sundered in the ultimate blow. The timeline for such an event depends on how phantom the dark energy is. If it were just slightly more negative than 1 in its equation of state, the Big Rip might be trillions of years away, or not happen at all, if it tends asymptotically to a constant. If it's substantially more negative, the rip could happen sooner, though current data suggest dark energy is very close to a cosmological constant, 1. The concept is spine-chilling, the fabric of space accelerating so wildly that it rips apart anything bound. Matter is literally disassembled by the expansion of space. Most physicists consider this unlikely based on current evidence, but it's not ruled out absolutely. If our current best fit is slightly off, the cosmos might end not in ice, but in a singular crescendo of tearing apart everything. Another scenario, the Big Crunch. This is in a sense the opposite of heat death or Big Rip. It's a reversal of the expansion into a contraction. If, for some reason, dark energy were to dissipate or turn attractive, and if the density of matter were high enough, gravity would eventually win out and pull everything back together. The expansion would slow, stop, and reverse. Distant galaxies would start to approach rather than recede. Over billions of years, what was once an expanding universe becomes a collapsing universe. Galaxies would rush together. Clusters merge into a supercluster, superclusters into huge sheets, and finally all material closes in. The temperature of the background radiation, which had been dropping for eons, now starts to rise again as space compresses that radiation. The dark, quiet cosmos would light up once more as every particle of light gains energy and blue shifts. Galaxies might careen into each other with increasing frequency. The night sky would glow brighter and brighter as more galaxies cram into our observable view, and the heating of all gas triggers star formation, or makes existing stars shine more fiercely. In the far future of a Big Crunch, the universe's scale continues to shrink. What were galaxy superclusters a few billion years before are now overlapping and colliding. Eventually, all matter might coalesce into an extremely dense state. The temperature would soar to star-like or greater levels everywhere, ionizing whatever atoms existed once more. Fusion could ignite in giant bursts as gas clouds compress. Essentially, the reverse of the universe's expansion timeline happens. Clusters of galaxies collapse into blazing quasars, then into massive nebulae, then into a shrinking ball of plasma, then perhaps into conditions similar to the very early universe. If quantum gravity or other effects don't intervene, this collapse could lead all the way back to a state of seemingly infinite density and temperature. Essentially, a mirror image of the Big Bang, sometimes dubbed the Big Crunch. Is that truly an end, or could it be a bounce? Some modern theories speculate that a Big Crunch could transition into another Big Bang, the death of one universe seeding the birth of a new one. In cyclic models, the universe might undergo endless, or at least many, Bang Crunch cycles. Ancient cosmologies, like Hindu cosmology, imagined time as cyclical, cosmic days and nights of Brahma, with universes expanding and contracting periodically. A scientific version might be, after a crunch, all space and time re-expand again, maybe after reaching a singularity, or perhaps never fully reaching infinite density because new physics causes a rebound. If there is a bounce, the astonishing implication is that our Big Bang might not have been the absolute beginning, but simply the latest bounce. Some theorists working in quantum cosmology and string theory have explored models where, for example, our 3D universe, brain, periodically collides with another brain, causing big bangs in a cycle. Others, loop quantum cosmology, find that quantum effects could cause space to repel at extremely high densities, avoiding a singularity and starting expansion anew. If the universe can bounce, what happens to entropy and the arrow of time in such a cycle? That's a tough question. Naively, entropy would carry over and increase with each cycle, which would be problematic. You can't cycle indefinitely if entropy irreversibly accumulates, unless the bounce somehow resets the entropy or disposes of it. Some proposals, like conformal cyclic cosmology, Roger Penrose's idea, suggest that at the end of a heat-death scenario, when the universe is nothing but photons and essentially devoid of scales, it might be possible to relabel that state as the initial singularity of a new Big Bang. Since a universe of only structureless photons has no concept of time or size, it could be equivalently reinterpreted as a new Big Bang state. This is speculative and not widely accepted yet, but it shows how creative thinking is being applied to the idea of cosmic rebirth. There are also other theoretical fates. One is a vacuum decay scenario. Perhaps our current vacuum, the ground state of fields in the universe, is not the true lowest energy state. If there exists an even lower state, the universe could at some point quantum tunnel into that lower state. If that happened, a bubble of true vacuum would appear somewhere and then expand at near the speed of light, converting everything it touches into a new state of being. Within that bubble, the laws of physics might be different constants, particle arrangements. So essentially, it's like a new universe erasing the old one. This bubble nucleation and expansion would be catastrophic, from our perspective, and extremely fast. One moment everything's fine. The next, a bubble of alien vacuum is rushing through you, disintegrating you, Earth, and every structure. And we'd never see it coming because it expands at light speed. It's a wild idea, but certain particle physics models make it a possibility. For instance, if the Higgs field sits in a metastable false vacuum. Current data suggests it's not highly likely in the near term. If it can happen, it might be trillions of years away or more. Or maybe it's truly stable and won't happen at all. In any case, it's another way nothing, or rather a different something, could be born from our something, effectively resetting the cosmic stage abruptly. Finally, even in the heat-death scenario, some have mused about the possibility of random fluctuations creating new ordered patches. Given infinite time in a static de Sitter universe, the end state with dark energy domination, quantum fluctuations could occasionally, by sheer chance, produce a small region of lower entropy, perhaps even a new Big Bang seed, or a so-called Boltzmann brain, a spontaneously formed self-aware entity out of chaos. While these ideas are thought experiments and lead to some absurd-sounding consequences that physicists debate, often to argue that an eternal de Sitter phase might be problematic or that some new physics must intervene before infinity, they speak to the richness of considerations about eternity. Even in an endless nothingness, given unlimited time, perhaps a fluctuation might trigger a new creation event. The probability is incredibly low for any given moment, but in infinite time, the unlikely becomes inevitable. So perhaps heat death isn't truly the end. It could be a plateau before another beginning, in an endlessly cyclic multiverse of fluctuations. This is deeply speculative, verging on philosophical, but it shows that even finality might not be absolute. At this juncture, we've painted possible endings, eternal expansion into heat death, a big rip, a big crunch with possible bounce, or a transition to something entirely different. Each path carries different implications for the arrow of time and for the question of whether the universe has a purpose or just a lifespan like any other natural phenomenon. From what we can tell now, with our cosmological measurements, the most likely fate is an ever-accelerating expansion leading to a very cold, very empty universe. Heat, death. But our knowledge is incomplete. Dark energy could surprise us by changing behavior. New physics, like interactions between dark energy and matter, or a slow dilution of dark energy, could alter the story. Now, let's step beyond even these questions of our universe's fate and ask, is our universe the only universe? For much of our narrative, we presumed that the universe meant all that exists. But modern physics has opened the door to the idea of a multiverse, a larger reality in which our universe is just one part. There are actually different notions of multiverse that scientists discuss. One arises from quantum theory, the many worlds. Interpretation suggests that all possible outcomes of quantum events actually occur, each in its own separate branch of reality. In that view, reality continually splits into a vast ensemble of parallel timelines. That's a kind of multiverse, a branching tree of universes coexisting in superspace. It's a very different concept from universes separated by space. It's more like parallel dimensions or alternate histories. It might not affect our cosmic story directly, so let's set that aside after noting it as an intriguing possibility. parallel universes where, say, different events happened in history, etc., playing out side by side unbeknownst to each other. The multiverse idea, more relevant to cosmology, arises from cosmic inflation and string theory. If inflation occurred as our theories suggest, the ultra-fast expansion in the universe's infancy might not have been a one-time event that ended everywhere at once. There are strong reasons to suspect inflation is eternal. While it ended in our region, allowing our Big Bang fireball to proceed, in other far-flung regions, inflation might still be going on, endlessly creating more bubble universes. Picture a vast, inflating space-time, a kind of ever-growing foam. Occasionally, in that foam, regions stop inflating and crystallize into hot Big Bang bubbles like ours. Each bubble is a universe in its own right, with potentially different properties depending on slight quantum variations when inflation ended there. Our observable universe would be just one bubble that happened to nucleate 13.8 billion years ago. There could be countless others. These other universes are not located in our space. They are separated by continuing inflating space, which expands so fast that we can never catch up to the neighboring bubbles. They are forever out of reach. Each bubble might have different physical constants, particle content, even dimensionality, especially when combined with ideas from string theory. String theory suggests that the vacuum of the universe, the configuration of extra dimensions and fields, could have many possible states, sometimes quoted as 10 to 500 or more possibilities in the landscape of string theory solutions. Each bubble universe could realize one of those many possibilities. That offers a tempting explanation for why our universe has the peculiar laws it does. If there is a multiverse of all kinds of universes, we just happen to be in one that had the right conditions for galaxies, stars, and life, because otherwise we wouldn't be here to observe it. This is a kind of anthropic selection from a multiverse ensemble. It's important to note, none of this multiverse speculation is confirmed, but it is grounded in serious physics theories. Eternal inflation is a rigorous outcome of many inflation models. Once inflation starts, it generically doesn't stop everywhere, so while one bubble forms, inflation continues elsewhere, leading to potentially infinitely many bubble universes. And in string theory, the many possible shapes of extra dimensions, each giving rise to different physical constants, combined with inflation, virtually guarantees a multiverse. The inflating space fills itself with regions realizing all those options. Can we detect or observe evidence of other universes? It's challenging by definition. If they are truly separate, we can't see into them. But one possible sign would be if a neighboring bubble universe in the early inflationary period happened to collide with our bubble. That collision might leave an imprint, perhaps a circular pattern or a particular kind of distortion in the cosmic microwave background. People have actually searched CMB maps for hints of such collisions. So far, none have been convincingly found, but the search exemplifies how we don't shy away from trying to test even outrageous-sounding ideas. Another hint could come from the distribution of gravitational waves or subtle effects on the distribution of galaxies, none detected yet in a way that screams other universe. Another multiverse notion comes from higher dimensions and brain-world scenarios. String theory requires extra spatial dimensions, 6 or 7 beyond our usual 3. Those dimensions could be compactified, curled up small, or in some models, we could be confined to a 3D brain floating in a higher dimensional space. There could be other brains, essentially other universes, separated from ours in the extra dimensions. Normally, we'd have no interaction with them except perhaps gravity, which can propagate in the higher dimensional bulk. Some have even imagined that a collision between brains could be what the Big Bang was. 2 3D worlds collided, releasing energy that flooded our brain with the hot matter of a Big Bang. If those other brains, universes, exist, they are right next door, in a sense, perhaps only a tiny distance away in a 4th spatial dimension. but we can't see them or touch them because our particles and light are confined to our own brain. It's a mind-bending concept. Other entire universes, potentially a millimeter away from us, in a direction we can't perceive.
Whether it's bubble universes, parallel quantum worlds, or higher dimensional brain worlds, the multiverse idea profoundly changes the context of our cosmic story. Our universe could be a small chapter in an infinitely larger ensemble. It could mean that what we consider the ultimate beginning, the Big Bang, is just one local event in an eternally evolving multiverse. And it forces interesting questions. If there are countless universes, each with possibly different physics, what does that say about meaning? One could imagine each universe as having its own narrative, its own potential for life, or even intelligence. Are there other conscious beings out there, not just in our universe, perhaps in distant galaxies, but in entirely separate universes, forever causally disconnected from us? This drifts from science into philosophical wonder, because by construction, we may never verify those other universes. Yet, the theories that predict them, inflation, quantum mechanics, string theory, are in principle testable in other ways and have earned credibility. So we take the multiverse seriously while acknowledging it currently lies at the speculative frontier. Regardless of whether there's a multiverse, we find ourselves in this universe with its particular story. From a singular beginning, or at least an extremely hot, dense early state, our universe expanded, cooled, formed structures, and eventually produced us, beings capable of reflecting on the whole process. We've gone from contemplating mythic cosmologies to actually measuring the geometry and expansion history of the cosmos. We discovered the universe had a beginning, Big Bang, that it is 13.8 billion years old, that it expands, that it has a cosmic web of structure, and that it is dominated by dark matter and dark energy. These are incredible revelations, won through the hard work of observation and theory, building on generations of curious minds. Now we turn to the philosophical and existential implications of the cosmic story. Standing under the night sky, we can feel two seemingly opposite emotions: insignificance and profound connection. On one hand, the universe is vast beyond imagination. The Earth is a tiny pebble in a gigantic space. Even our galaxy, with 100 billion stars, is just one in a sea of billions of galaxies. Physically, we occupy no privileged position. The cosmos is not arrayed with humanity at the center. We are off in a corner of an average galaxy, which itself is in a supercluster that is unexceptional among others. Time-wise, human history is an eye blink compared to cosmic time. The stars shone for billions of years before we came along. They will continue billions of years after we are gone. It's humbling, even daunting, to recognize this. The famous pale blue dot photograph taken by Voyager 1 from beyond Pluto, showing Earth as a tiny bluish speck in the void, encapsulates that humility. All of human history, every joy and sorrow, every hero and villain, played out on that mote of dust, suspended in a sunbeam in the vast darkness. When confronted with such scale, it's natural to feel small. Yet, on the other hand, how marvelous that we can comprehend this scale. We are made of particles that were forged in stars. Essentially, the universe gave birth to conscious organisms that can observe and contemplate the universe. We are a way for the cosmos to know itself, a sentiment popularized by Carl Sagan and profoundly true. Our atoms originated in the Big Bang, hydrogen, or in stellar furnaces, carbon, oxygen, nitrogen, etc., or in supernovae, iron, zinc, iodine, gold, all the heavier elements. We are literally children of the stars, made of stardust. Through us, the materials of the universe have become aware and curious. That imbues us, and possibly other intelligent life out there, if it exists, with a kind of cosmic significance, albeit a self-bestowed one.
We carry the legacy of 13.8 billion years of cosmic evolution in our bodies. When we gaze out at the galaxies, those galaxies are in a sense observing themselves through our eyes. The emptiness of space, while vast, is not completely empty. It's filled with fields and particles and possibilities. Likewise, the perceived emptiness or pointlessness one might feel when confronted with a giant, cold universe can be filled with our own meaning and purpose. The cosmos doesn't hand us a script. Instead, it gives us the stage, the raw materials, and the invitation to create meaning. And humans have been doing that for as long as we have existed, through story, science, art, love, and exploration. We find that the more we learn about the universe, the more beautiful it becomes. Consider the fact that the atoms in your body were once inside of a star, perhaps many different stars over the eons. In a very real sense, you are as old as the universe, because the matter that composes you has been around since the beginning, apart from some recent transmutations via nuclear reactions. We are deeply connected to the cosmos. Every breath you take contains atoms from all over Earth and beyond, even some noble gas atoms that were forged in the Big Bang. The water you drink contains hydrogen made at the dawn of time. The calcium in your bones was fused in some star that ended its life long before Earth formed. We are a microcosm of the universe. This perspective can evoke a sense of spiritual awe, even in a non-religious framework. It's the awe of existence itself, the recognition that we are part of something vast and magnificent. The American astronomer Harlow Shapley said, "We are akin to the totality of things. The atoms don't belong to us, we belong to them. We are a moment in their journey." The universe's story also imparts lessons. One is the transient nature of all things. Stars are born and die. Even galaxies collide and merge. The universe evolves. Change is the rule. On Earth, we see that civilizations rise and fall, species come and go, all part of that cosmic change. But amidst change, there is continuity. The continuity of matter and energy, and the continuity of information passed on. Our sun inherited matter from previous stars. We inherited molecules from Earth's past life. We pass our atoms back to the Earth when we die. It's a kind of immortality, not personal immortality, but the persistence of our substance and our influence. A star that died billions of years ago in our region of the galaxy, by dying, it seeded the cloud that formed our solar system. In a way, that star lives on through us. Likewise, the choices we make and the knowledge we gain might propagate far into the future, indirectly shaping things we will never see. When we build a telescope and discover something, that knowledge changes the consciousness of humanity, which may alter our future actions and fate. Our cosmic understanding has also, interestingly, circled back to some ancient wisdom. Many cultures intuited a connectedness of all things, or a cycle of creation. The scientific specifics we've learned differ from the myths. The universe isn't literally the egg of a giant bird, for instance, but the emotional thrust that we are part of a greater whole is affirmed more strongly than ever by science. We now see that the same physical laws apply everywhere. We've sent probes to other planets and found familiar chemical processes at work. We've detected light from atoms in distant galaxies and found the same spectral lines as atoms we study in labs. The universe has a unity, and the story of cosmic evolution is a single, continuous narrative from the Big Bang to the present and onward to possible futures. We are a chapter in that narrative. In contemplating the end scenarios like heat death or Big Rip, one can feel despair. Will it all amount to nothing? But one might also find liberation in it. The distant future is beyond our control. What matters is what we do with the time and universe we have. The fact that the universe will end in one way or another does not negate the preciousness of its present. In fact, it enhances it. Just as mortal beings find meaning in life partly because it is finite, the finite window of a lively universe can galvanize us to appreciate its wonders all the more. We live in a cosmic springtime, when conditions are just right for complexity and life. It will not always be so, but how fortunate that it is so now, and that we are here to witness it. There's also a school of thought that even if our universe fades, perhaps life, or an advanced form of intelligence, could in some way continue or influence beyond its own universe. Some speculative ideas suggest extremely advanced beings might even hop between universes, or create baby universes artificially. These ideas blur science and philosophy and remain in the realm of imagination for now. But the mere consideration expands our sense of possibility. Perhaps the end of the universe isn't an absolute wall, but just another frontier to transcend for a sufficiently ingenious civilization. It sounds like science fiction, and it certainly is right now, but who can definitively say what a Type 3 or Type 4 civilization, if it could exist, might achieve after millions or billions of years of evolution? Bringing our thoughts back to the here and now, the night sky. It connects us to all of this grand history and future. When you next stand under the stars on a clear night, think about the journey of a photon that enters your eye. Perhaps it left a distant galaxy when that galaxy was young and our planet not yet formed, traveling across expanding space for tens of millions of years, through voids and past clusters, until finally, one night, it ended its journey on your retina, triggering a chemical reaction that led to an image in your brain. In that moment, you, a being of stardust, assembled on an 8-planet minor system around an unremarkable star, catch a whisper from the other side of the universe. And with collective effort, humanity has learned to interpret these whispers, to tell a coherent story of how we came to be. The cosmos is mysterious and beautiful. Every discovery seems to open new questions. We determined the age and shape of the universe, only to find most of its content is invisible, dark matter and dark energy. We may solve dark matter, perhaps a type of particle, and dark energy might remain puzzling or turn out to be a property of space itself. We look for potentially habitable exoplanets, wondering if life arose elsewhere. We tune our radios for possible signals from other civilizations, not knowing if we are alone or one of many. We delve into the quantum foam, attempting to reconcile general relativity, our theory of the very large, with quantum mechanics, the theory of the very small, hoping for a deeper understanding that might unify forces or reveal why the Big Bang happened the way it did. The quest goes on. Through it all, there is a human element that persists: wonder. As the astronomer Maria Mitchell said, "We reach forth and strain every nerve, but we seize only a bit of the curtain that hides the infinite from us." Yet, that bit of curtain has revealed an awful lot, and we continue to gently pull at it. Will we ever see the infinite, or the true beginning, or the full scope of the multiverse? Perhaps not, but the pursuit is part of what makes us human. The same impulse that made our ancestors paint constellations on cave walls and craft stories of creation now drives rockets and equations toward the heavens. Ultimately, the story of the cosmos is meaningful to us because it is also our story. We are not mere spectators. We emerged from this grand process. The hydrogen in our bodies, in every molecule of water for instance, comes straight from the Big Bang. That means a part of us is as old as time. The carbon in our cells was forged in stellar hearts, making us the heirs of those stars. When we die, our atoms will return to the Earth, and eventually some will drift out to space again, maybe to become part of a new star or planet eons hence. In that sense, we are immortal, though our forms are temporary. So, what does it mean to be born from nothing? It means that existence is a gift against all odds, a tiny realm of something in an infinite sea of nothing. It means that perhaps nothing is unstable or pregnant with potential, that even a void can give rise to worlds. It suggests that reality is not a static block, but a dynamic story. Our universe began in a state devoid of structure, grew into a vast living tapestry,
and will either continue to expand and evolve in complexity for some time, or eventually simplify again into quiescence. We got to observe a rich segment of that timeline, full of galaxies and life. That realization can fill one with a sense of reverence, not in a religious sense, but a profound respect for the majesty of nature. As our journey through the cosmos comes to an end, let's reflect on where we are. A small planet orbiting a medium star, on the edge of a galaxy that has at least 100 billion siblings, in a universe of maybe 2 trillion galaxies within our view, each brimming with stars and possibilities, all governed by the same physical laws, all born together in the same primordial explosion, all fated to either drift apart forever or perhaps crash together in some finale. We, ephemeral yet remarkable, stand here and through ingenuity have uncovered this story. It is a continuous, cinematic, emotionally resonant story, one that stretches from the beginning of time to the very ends of imagination. It's a story told by starlight and cosmic background whispers, written in equations and in the awe of anyone who looks up at the midnight sky. It's the story of the cosmos, our story. And though this particular telling of it must now conclude, the story itself goes on, written in the galaxies overhead and the atoms within us. As long as there are thinking beings to wonder and explore, the narrative will be retold, refined and cherished anew. In that sense, the cosmic story truly has no end. It lives so long as curiosity lives. So take a moment to step outside on a clear night. Feel the cool air. Look up. The light hitting your eyes has traversed the universe to reach you. The atoms in your body resonate with the history of the cosmos. The void may be vast, but you carry within you a universe of understanding that fills it with meaning. In the silence of the night, you can hear, if you listen closely, the echoes of the Big Bang and the songs of ancient starlight. The story of everything is speaking, and through our minds and hearts, the cosmos is listening to its own tale. In that communion, between the cosmos and our consciousness, lies a profound truth, that we are not apart from the universe. We are the universe, in small but significant part, and its fate and our fate are intertwined. From nothing we came, into nothing, or something beyond, we may go. But in between, we have the chance to witness and marvel at the grandest of spectacles, existence itself. Let us be grateful for that chance. Let us keep the cosmic perspective, allowing it to illuminate our lives with both humility and wonder. And let us continue the journey, always, for as far as mind and imagination can reach, embracing the mystery and majesty of the cosmos. The cosmic saga continues, and we are fortunate narrators within it. The final line is not yet written.